Yes. Can you hear me,
Just
Professor Pomorsky? We can see your presentation. You can start, please. Take your floor.
yes, can you hear me? I cannot hear you.
Please start. We can hear you well and see your presentation. Dr. Pomorsky, can you hear us?
Hear me?
Yes, we can hear you. And we also saw your
Yes, I'm sorry. I have problems with voice, and now is my presentation visible?
Yes.
All right. I'm sorry for the problems. Good morning to everybody. So it's my great pleasure to give a talk on hybrid superconducting semiconductor quantum hardware and quantum electronics. My name is Krzysztof Pomorski, and I am from Łódź University of Technology and also represent the company Quantum Hardware Systems. Okay, so let me proceed. So basically, I will give very short introduction to current status of quantum technologies, and I will focus on a description of two semiconductor closed loops that can interact inductively and electrostatically. And also this system will be later integrated with superconducting electronics. So I will briefly describe the motivation behind my research. So right now that we observe very rapid progress of development of quantum electronics, especially quantum IBM experience, and nevertheless there is a recovery of Fujisawa work on single electron devices in a semiconductor. So there are new kind of schemes for CMOS, for quantum CMOS implementation. And this is a kind of driving factor for me. So basically, as you know, there are different types of schemes for quantum computers, more than 20. And actually, so right now the dominant is referring to Josephson junction, but still we have ion traps. And also we have a semiconductor quantum dots. And there are two ways of usage of that, by spin-based quantum computation on quantum dots and by usage of single electron devices. I will somehow refocus on usage of single electron devices, so like usage of electrostatic channels of interaction. So basically what we have is right now is we have downscale of the size of CMOS gates of transistor. So right now the channel length of transistor is is less than 10 nanometers on the commercial, and new applications are coming with like 7 nanometers of channel length. And this opens a perspective for functionalization of transistor into qubit. So basically what we have is that we can use source as one quantum dot and drain as another quantum dot. And then we can have movement of electron between those two kind of quantum dots. And then there is a different framework of a quantum information processing. This is like position-based in quantum information that is a kind of different from most common use mainstream, which is based on eigenenergy levels. So basically, if you want to have a qubit operational, you need, in the same way as it is before, in eigenenergies, you need at least 2 energy levels to be occupied. But here, what is essential is maximum localization on left and right side. So basically what you have is then having 2, so you can classify the region, this region to be corresponding to region 0, to logical 0, and another region to logical 1. In such type of qubit, you have inherent oscillation between left and right state. And then this oscillation frequency is proportional to energy level difference. And this qubit starts to be more and more popular quite recently, but because this is more suitable for a quantum information processing, and this is because the size of nanowires can be very small, like much smaller than the size of solenoids used for IBM quantum experience. So basically, you can translate all quantum information processing from eigenenergy level qubits to position-based qubit. There's a special kind of rotation matrix, which does describe this process. So the advantage is the size, the disadvantage is a charge, noise, and other factors that can be compensated. So then also in this such type of scheme, you can create interface between Josephson junction and quantum dot system. So at the top, it's given Josephson junction system where you have a left superconductor, right superconductor, and there is an area where Andrew bound state does exist. And this system interacts with 2 quantum dots, so that are given at the bottom. And then what happens is that there is Andrew bound state deformation, since one electron moves back and forth, and it generates time-dependent electric and magnetic field. So due to this Andrew bound state deformation, you can construct electrostatic interface between semiconductor quantum electronics that is beneath and between Josephson junction that is above. And then you can go further. So you can basically think of on electrostatic interface, which is depicted on the right side. So you have a semiconductor nanowire. On the top, there are gates with insulation in between. And at the bottom, you have a Josephson junction, which is Cooper pair box. So you can have this interaction of Cooper pair box with this single electrons in semiconductor nanowire. So this is electrostatic interface. On the other hand, you can consider inductive modes of interaction, and then in such a case, you have a semiconductor nanowire, which is red on the right side, and this semiconductor nanowire does interact inductively with closed loops of superconductor. So in that way, you can have inductive interface. Well, one should remember about quantization of magnetic flux in a superconducting ring and in semiconductor ring, so that there is different value of flux quanta is h/2e in superconductor and H/E in the semiconductor. So that's quite essential. And also the size of the systems is bit different. So one have to take it. And then this brings me to the problem of two interacting protons. So you can state the problem in a very simplistic way. You have semiconductor nanowires. You place charge board inside, and then you can have inductive interaction, and also you can have electrostatic interaction. So this problem can be well described classically, but this is a bit more troublesome to go into quantum mechanical description. And there are two ways. I will start from a kind of with self-consistent approach. So let's say you have two electrons, so the position is parameterized by phi1 and phi2, and there is a wave function of each electron. So actually, this moving charge ball generates vector potential that affects this one and reverse. So that's why you can construct the Hamiltonian that is dependent on the state, and this is the case over here. So here the psi2 phi2 is a wave function, psi1 phi. So there are two wave functions. So this is like a nonlinear Schrödinger equation problem. And then by having self-consistency by iterations, you can approach the solution. So that's one of case of the numerical computations. So you can see a certain level of anticorrelation of electrons due to inductive interaction. So there's another type of results in that direction. And then you can have slightly different approach basing on Hilbert product of two spaces. In that way, the Hamiltonian is linear. So in such type of case, you also have electrostatic interaction. You can also observe anticorrelations of electron positions. So this is how this problem is being tackled, and it's still under further considerations. So I believe we can. So that's this attempt, which I described in description of inductive interface between semiconductor and superconducting electronics. Okay, so I guess my time is kind of finished, right? I supposed to finish right now. So shall I take some questions or remarks?
Thank you very much for very important report. And if someone have in our conference hall question.
Hello. I have one question about the definition of. I have one question deal with definition of words rotons. Why do you call this situation rotons, and what is the comparison with rotons in helium-2?
Okay, well, maybe there is, let's say, okay, so we have a quantization of angular momentum, essentially, you can say. So it's like linear qubit. I call it circular qubit, not linear. So you have the periodic boundary conditions which describe it, and so there's a certain quantization and then so it's okay. So you can have two types of qubit. You can have linear qubit, which is just nanowire with gates so let's say you have two regions and you have gates on the top. I call it linear qubit. So linear qubit can be essentially controlled by electric field mostly. And in case of roton, you have possibility of using both electric and magnetic field. So this might give you certain advantage from that perspective. Well, it's like transmon. transmon in superconducting electronics, you can have control by electric and magnetic fields also. So in a sense, I tried to describe the evolution of this problem towards such type of architecture geometries. In regards to Roton in a superfluid, well, I would say difference is because you have Gross-Pitayevsky equation, right? And so which is nonlinear kind of Schrodinger equation. And here this problem can be linearized as well. So that's very different. I'm not sure if there exists better name for the system which I described. So if yes, please let me know.
Thank you very much for your contribution and also for interesting question. And the next our speaker will be Professor Dmytro Kharchenko, please, from Institute of Applied Physics of the NAS of Ukraine.
Okay. Hello, everyone. I'm very glad to have this talk and this day today. You know, today is Day of National Flag of Ukraine, and I'm happy to have my presentation in this conference. Okay, let me check. Well, I should. No. Okay. Thank you. Okay, so I will speak about some properties of ferrum. We call it FeCRAL. It's ferrum chromium aluminum alloys, and what happened in this material. Why we consider this material at first. This material became very important after Fukushima incident, when you know we have a big problem with zirconium cladding materials in the reactor, which makes a lot of problem for all the community, for nuclear power scientists, and it was a problem to find a new material and substitute all zirconium tubes, which considered as cladding materials, where we put uranium platelets or fuel and generate the electricity for as a most, let's say, cheaper and most okay, not dangerous for our planet. And this material is used because of the properties, like it can be used for high temperature construction, and it has a good oxidation resistance. And as I said before, it is considered as a new kind of material to substitute zirconium-based alloys. And why this material has a good properties? Because it has doping like chromium and aluminum, and they make some protective layers. And the second problem that, you know, in such kind of study of material for nuclear power engineering or nuclear power plants, every time when we want to improve some properties, we add some elements, but there is additional side of the medal that when we improve something, we make some problems. Additional, we meet some problems which comes when we improve something, we destroy something else. So it's a problem to find the content of doping like like chromium and aluminum to make material more stronger and for radiation-induced hardening or resistance for oxidation resistance and to improve the material properties. The next, what we deal with, why we deal with this alloy. Yeah, chromium and aluminum can increase resistance, oxidation resistance, but chromium precipitates into alpha prime, precipitates with the same structure as a matrix material, I mean iron, but these precipitates, alpha prime precipitates, they make they pin some dislocations and increase the hardening of material and make some brittle phases like alpha prime phases, and materials became more brittle. So plasticity, we just lose the plasticity of material, and material can be broken when we put it into a reactor, and because of formation of large amount of point defects, large amount of clusters, and these clusters and point defects makes dislocation loops, which additionally increase the hardening of material. So why we are speaking about this material here in this conference? I will speak about this systems because this small precipitates, like you see on the right side, this of violet color, it's a chromium precipitate. The size is around 4 or 5 nanometers, but the amount of these precipitates is too large, and they can be formed during irradiation. And dislocation can be pinned on these precipitates. That's why material became hardening. Additional, this is the right picture illustrate the dislocation loops. It's like platelets or additional atomic plates, planes which incorporated into the crystal structure. And these loops, again, of the small size, like 10 nanometers or 20 nanometers, but a large amount of these defects, again, increase the hardening of material. When these loops evolve in time or during irradiation. As far as we consider the system in a reactor, we consider that this material is in non-equilibrium, extremely non-equilibrium conditions, and all processes that can be observed here are very complicated, and they connected to each other. So it's very complicated system. So we should consider, when we want to study the change of microstructure at irradiation and evolution of defect structure, we should take into account everything, starting from diffusion motion of atoms and ballistic motion of atoms when a neutron or other particle can disturb some configuration and hit the atom moves to another position. Then we can find a lot of point defects which can coagulate and form some clusters or make some dislocation loops. And this interaction of precipitates with dislocation loops. So all this process should be considered all together, but it's very hard to describe all system altogether. But anyway, some ideas which we implement in our simulations and in our study, I will want to show here. So formally, in what way the calculations and simulation were done? Oh my God. Okay. So we consider the concentration of all our elements is 3, and consider dislocation, consider point defects like vacancy and interstitials, the clusters, and consider dislocation loops, so it can be in two directions in this system. We consider the sinks of point defects like grain boundaries and dislocation loops and precipitates where these point defects can move to these sinks, annihilate, and the microstructure formula can be changed even from mathematical point of view, but a lot of experimental studies illustrate that really a microstructure can be changed under radiation. And here I want to show in what manner it can be done. So to study a specific kind of system, we should use specific kind of thermodynamic potentials. In our study, we use SGTA database. It's scientific group Thermodata Europe database, where we use some potentials and use the method of Calfadi's well-known method for calculation phase diagram according to experimental data, and use some data from atomistic modeling to describe defect structure. So formally, we we consider the reaction diffusion problem with different kind of fluxes and reaction terms describing the production of defects and relocation of atoms during irradiation, and want to study in what manner the structure can be changed. And the main idea is to find how this nano size object can change the microscopic properties. I will speak about hardening in the final of my talk. Okay. It's very hard to see this presentation. It was made in PDF. Okay. Anyway, so we consider the atomic end defect system, subsystems, consider the mole concentration of all elements and concentration of defects shown as CD. We consider the Gibbs energy functional, which is divided into kind of potential. One described the alloy components and one described the defects. Alloy components or constituents are shown described by typical reference energy, entropic part, and interaction part with interaction energies or coefficients L, M, mu, nu, C. And defects considered in the same manner, but here we consider the interaction of defects with the atomic system and, of course, gradient energy constructions. And for all of coefficient, we use the parameters shown in database for material. When we consider the evolution of, let us consider evolution of alloys constituents. So we consider the thermodynamic motion or thermodynamic forces, and consider the ballistic forces. Thermodynamic comes from ordinary thermodynamic fluxes, and ballistic exchange is some kind of diffusion process when atom can be heated by bombarding particles, change the position in some distance, and then can move back or, let's say, stay in this position. So radiation here results in production of structural disorder, but without a loss of material or production of material. So anyway, the mass conservation law here works well. Additionally, to describe the radiation influence, we take into account radiation enhanced diffusion, because a lot of point effects produced during irradiation, and diffusion coefficient becomes much more larger than we have for, let's say, equilibrium system without radiation, where we have equilibrium point effects. So finally, we deal with equation number 3 for atomic concentration with thermodynamic flux and ballistic mixing. And when we consider the point effects, or we consider again the diffusion flux of point effects and reaction terms, the reaction term which describe the production of point defects with production rate K nRT. It's standard dose rate, which can be computed according to the energy of arriving particles and the mass of these particles, and consider this point defect sinks. So the reaction part is shown after equation 4. You see this production. The first one is production. The second is annihilation and sinks, and the last one is recombination, like interstitial recombined with vacancies. Of course, here we understand that we have different kind of dislocation loops, precipitates, shown as RP. This is mean radius of precipitates, and NP, this is number of precipitates, which we should calculate automatically in our simulation code. We assume that this constant like Z, they are known as preference constant, which depends again on the size of dislocation loops and size of precipitates. So to describe the dynamics of dislocation loops and the number density, we use the formalism shown in equation number 5. It's very hard to see because some symbols are missed here. But it has the common structure. The first time for radius of dislocation loop, the first equation in 5 describe the net flux of defects. The second term with K describe the production of loops according to formation of defect clusters. And the third, the last one describes the annihilation of loops when they come together with each other. And the last equation describes the number of dislocation loops, how it can be produced. Again, they can be produced from defect clusters, again, with the relaxation term that I speak before, and the emission of vacancies from dislocation loops. Here we take into account that we have the multi-grain structure, so the limitation of formation of dislocation loops is given by the function G. That's the last one here. So here it's mean that this function controls the speed of growth of dislocation loops. So in our modeling procedure, we consider all things which we can include in our simulation code according to the time scale. So motion of atoms, or we consider concentration of atoms, of course, concentration of defects, and we consider self-consistently evolution of dislocation loops and their number density. Number of precipitates and their size we control by our simulation procedure. So at first, anyway, in this simulation procedure, we consider 2 stages. We, according to the typical procedure of exploitation of materials, so we need to prepare the target at first and then put it into reactor. So the first, we want to see how, in what manner and how elements can control, how we can control the microstructure when we change the temperature or concentration of elements. When we prepare the target. So we see here the phase diagram illustrating that we increase the temperature, the domain of phase separation is decreased. So you see when we change the concentration of chromium, we can see the size of a domain for phase separation decreases with temperature. So this is a phase diagram when we can choose our material and then put the corresponding macrostructure into irradiation. This is typical snapshot illustrating formation of this microstructure for specific kind of alloy. Just put it only one, ferrum 30% of chromium, 5% of aluminum at temperature 700 Kelvin. And you see the distribution of alloy elements of chromium in the first row, and the last illustrate the aluminum, equilibrium vacancies, and interstitials. So the main idea is to use this microstructure in a reactor and consider in what manner it can be changed. But the first, some words about chromium and aluminum, that when we increase the aluminum and chromium content, the time needed to start the phase separations, so speaking about emergence of chromium precipitate, decrease rapidly. But you see the size of precipitate increase in the same manner dependently of the concentration of aluminum and chromium. So practically in the same manner. And distribution of precipitates follows the standard Lifshitz laws of Wagner law. So these data concerned about how we can prepare our targets. And you see in what manner elements can change at least the time scale for phase separation. But anyway, we consider only one alloy to put it into reactor. And the first very important result that comes from a linear stability analysis, when we have the phase diagram shown as dotted line here, typical phase diagram for ferrum chromium aluminum alloy, and you see when we put into reactor with dose rate like with dose rate, it's 10 in -6 displacement per atom per second. So we see the phase diagram totally changed. So we have, at least we have 2 or 3 part of phase diagram depending on the distance of relocated atom when it was heated by a neutron. The distance is known as dr here. Is the solid line belongs to when the distance is equal to the lattice constant. And when we increase the distance, we don't know exactly this value, but we know that it's similar of several lattice constants. But you see what happened here. So when we can have the solid solution, in the first case, we have the solid solution and the phase separation domain in phase diagram. But when we increase the this relocation distance, we have the additional domain. It's composition patterning. And the diagram on the right side and B diagram illustrate that we can change the main parameters which control the radiation temperature, and the dose rate. So we see that a new kind of microstructure can be formed. The C, D, and E plots illustrate the stability exponent, which illustrate that we indeed we deal with phase separation when we have the instabilities from 0 K values like long wave instabilities for phase separation, and the E plot show that we deal with phase composition pattern when we have the limited number of K numbers where instability can be formed. So the question why we choose the dr like relocation distance, it depends on kind of particles: neutrons, protons, ions, heavy ions, etc. So with increase the mass of the particle, this distance increase. But this distance can depend on temperature and dose rate. It's very important. It is not discussed in literature now, even now, but in our simulation we found these results. I will not speak about it here. In what manner we consider the we can observe the phase separation and patterning. The A row illustrate the typical scenario for phase separation when we have the domains of chromium-rich precipitates, and these precipitates increase in time. This is the solid line on the C curve. But on the composition patterning, this is the second row, you see that precipitates grow up to some specific size, and this size don't evolve in time. So system comes to some non-equilibrium, some equilibrium to some stationary structure which can be controlled by radiation conditions. So these precipitates will not grow. You see the line, the dashed line on C, D, and E plots. Plot C illustrate the precipitate size, the precipitate size according to the first row. It increased by the number. There's D plot. Illustrate the number of precipitate decrease because they start to collide and interact according to Lipschitz-Slosser-Wagner mechanism. But for the composition pattern, we see that the number of precipitates goes to some stationary value. But this result concern when we use the initial conditions like totally homogeneous alloys, or let's say solid solution, we decrease rapidly the temperature and put it into reactor and consider what happened. But the main idea is what will happen when we have the initial microstructure from our initially prepared target. So here we say we have two different scenarios. The first row, this B plots, illustrate the phase separation. So initial chromium precipitates start to grow. And again, this is the solid line in D plot, illustrate that precipitate grow during irradiation. But when we increase the relocation distance and go to the composition pattern domain in phase diagram, you see the initial microstructure a little bit destroyed, and a new precipitate can be formed. this number of precipitate you see on the E plot. And the content of chromium inside this precipitate is a little bit lower than we got in phase separation domain. So we see the microstructure is changed depending on the radiation conditions, of course. And here we can consider the concentrate in what manner aluminum is organized in our system. So it's totally dissolved, but chromium precipitates here are formed because of some chromium can go out from native precipitates and form new kind of precipitates inside the bulk due to emergence of defects in our system. But the main question is about how microscopic properties changed. Here I will show, I show the loop density, number density, loop radius. You see, it's well correspond to experimental data in different direction. And figure 9 illustrate the hardening change. You see that during the irradiation, the microscopic properties like hardening, which describe the brittleness of material, the hardening increased up to 0.3 gigapascal, even at doses around 10 dPa. So this small, the main result comes from that small objects like precipitates, chromium precipitates, and dislocation loops can essentially increase the hardening of material and change the properties. So finally, conclusion that I will not speak because I have no time, yeah? Just some words. So result that we obtain here correlate well with experimental observations and can be used for additional studies of these materials and can be used for to correct some models which were developed without self-consistent evolution of defect structures. Okay, thank you for your attention.
Thank you very much, Professor Harchenko, for this detailed analysis and very interesting presentation. And I would like to ask our participants about question. We have a couple of minutes for short question. Please.
Please say about experiment agreement with experimental data, your calculation. Exists experiment, direct experimental data for this phenomenon?
Yes, absolutely, absolutely. So here I put some numbers here, but I have not put the figure which illustrate the agreement. But anyway, what I want to say, the size of loops at these doses and the size of loops in different directions are of the same the same value. So the size is around 10 nanometers, size of loops, 10 nanometers, and this for 100, and it's a little bit higher, at least in eight times higher for loops in 111 direction. Because experimental data, you know, in neutron irradiation, it's very long-standing experiments. It's very long-standing experiments. So most of experiments are done by ions because it's very fast. We have very huge dose rate, like 10⁻³ in neutron. In our reactors, VVR, it's 10⁻⁸ dPa per second. So five orders, it's in VVR reactors. But in LVR, like light water reactors or scientific reactors, not commercial. So this dose rate can be increased, but we have not so many data to compare. But anyway, some data which we have, we can say that the loop size is in eight times larger in one direction than in other one. But anyway, other parameters that we used in our simulation comes from atomic modeling. So we believe that it should be. But anyway, the hardening is around the same. The hardening is around the same. And the size of precipitates and the number density is around the same. Thank you.
Thank you again. And the next, our speaker will be Professor Alexander Krivchikov from the Institute of Low Temperature Physics and Engineering of the NASA of Ukraine. With the report low temperature heat capacity of low dimensional carbon allotropes. Please. Take your floor.
I am Alexander Krivchikov, working in working low temperature institute in Kharkov. I study the thermal properties different solids. I study thermal properties different solids at low temperature. I present very interesting system. It's diamond composite. It's thermal properties, heat capacity for different diamonds. Prepare different methods. My report is connected with new experimental data. For nanosystem, nano diamonds, micro diamonds, produced in different waves, and then treated thermal treated and deeper different pressure condition. After that, measured heat capacity. You know the carbon possible exist in different algorithmic forms. Very famous, it's diamond, where exists sp3 hybridization. Diamonds, it's highest, very famous crystals. Another crystal form is graphites. It's another hybridization sp2, and exist a very interesting system with sp hybridization, and this system usually it's bulk materials, and graphite it's a strong anisotropic layer system, and between this diagram exists another form. It's like carbon nanotubes, different system amorphous materials. Now we in my report we study diamonds produced by graphite, and then during the graphitization observed the transformation again diamond to graphite. Typically, the sample nano sample is polycrystals, consist with diamond, with a huge boundary system, and we study nano diamond and micro diamond, different sizes. And if exist transformation diamond to graphite. After transformation, you produced completely graphite system. It's impossible because the diamond stable at high pressure and high temperature. And normal condition, the stable state is graphite. And during transformation, from diamond to graphite begin on boundary, on boundary system. TEM picture show directly the diamond structure inside diamond, and graphite outside boundary and transformation. Of course, this graphitization process studied different methods: X-ray, Raman, electroproperties. But we study these properties using low temperature heat capacity. And why? Let's see. Heat capacity from temperature. This is heat capacity of diamond. Diamond has the lowest heat capacity in general, and enough low temperature, it's behavioral typical T cube. It's Debye behavioral. But if you study heat capacity of graphite, you observed another behavioral. The graphite crystal has more higher, 10 times more heat capacity, another temperature dependence, and at low temperature exist linear term connected with electron conductivity of this system. But no information about the phenomenon graphite with diamond during the rectification process. Experimental data of heat capacity, you measure it using PPMS system from temperature region from 2 Kelvin up to room Kelvin. For this method, use relaxation method. The sample, it's milligram samples set up on the special platform, and then automatically measured heat capacity in temperature region. You study the sum produced 3 different methods. First is sintered amount materials produced by spark plasma sintering at enough temperature, and then annihilate and different temperature from 1400 Kelvin up to 2000 Kelvin. First, you produce the diamond, white powder, and during the annealing, the graphite on the boundaries, it changed color. Then temperature increased, then more higher graphite, and then the black, color became black. Another method to produce the graphite is detonated method, produce detonated nanodiamonds and different temperatures, different pressures. Another method, it's method directly synthesis diamond from graphite under high pressure. First, I show you result connected with micro diamond. It means the size of crystallized size is typical microns. And let's see 4 different samples. And green samples, it's produced enough aniline from enough low temperature, and show the begin process of graphitization. This graphitization process very strong influence on heat capacity. And next curve is the data for more higher aniline temperature. And star is connected with highest aniline temperature, 1900 Celsius. And very interesting, you found the completely different temperature dependence of this material compared to bulk diamond and graphite. And for 3 samples exist near cubic temperature dependence. This cubic temperature dependence, it's say about the layer materials is produced from this graphitization process different from crystalline graphite materials. Similar dependence of heat capacity observed in case nanodiamonds. Nanodiamonds show the 2 different characteristics. First, nanodiamonds annihilate at enough low temperature, 1000 Kelvin, show data similar to graphite with low temperature peculiarity. If you increased the aniline temperature, again appear T-square dependence. To understand this dependence, it's possible to imagine of structure of graphite. Here is present a layer structure, graphite produced during graphitization process. But in case nano diamonds exist peculiarity which say about the another carbon system. Possibly it's a lucid T-carbon system. It means that during preparation nano diamonds possible to produce not only graphitization system, but exist influence on diamond-like system. diamonds-like system, clear observed in case sintered nanodiamonds under pressure, and these materials produced from different conditions, pressure conditions at low temperature produce different temperature dependence. Let's see. T square, linear term, T 0 power 5, no temperature dependence. And mean there in nanosystem exists another subsystem, maybe T carbon loss structures. Exist the theoretical prediction of behavioral carbon system, heat capacity, and different dimensions. Mainly, the carbon materials has flexible dispersion law. It means the frequency quadratic depends on quasi inputs, and depend on this, depend on dimensions. It's possible to realize linear system with T dependence, heat capacity, proportional temperature, and in case of tree system, it's dependence typical cube. But in graphite system, possible to realize typical Debye dispersal frequency proportion Q. In this case, possible to realize T square dependence E to TP dependence. And maybe, and this system reflect this theoretical prediction. Direct X-ray scattering or sample detonated sample directly show, of course, exists the diamond in graphite reflection, but at enough low frequency, exists evidence about the like system, carbon or diamond. And conclusion. Heat capacity of nano and micro diamond different from bulk diamonds and crystalline graphites. Heat capacity reflects a complex low dimensional carbon structure produced in results that transformation diamond polycrystal into turbostatic carbon structure of graphite type. Unique low temperature dependence give new information about diamond-like or graphite-like amorphous structure also. Thank you for attention. And,
thank you very much for very interesting report, and I would like to ask our participants ask some questions for our speaker. Please.
So you can say that you have enough good agreement with existing theory of your experiments. So you have enough good agreement. Enough good agreement with your experiment and the existing theory. So you can say this.
I think the question is about theoretical and practical experimental data. A good agreement, yeah? It's with good. Mhm.
Of course, it's experimental data because measured for low temperature calorimetry. And for understand the new results necessary, compare with theoretic prediction of this system, because system very famous. In case of crystal system like diamond, graphite, and complex system, it's no directly theoretic calculation.
Thank you very much. I've seen that we have one more question. Yeah, please.
Thank you for a very interesting report. Could you comment frequently when we talk about diamond-like film, we talk about some mixture, diamond phase and maybe graphite phase. How you control your purity of sample when you talk about diamond properties and graphite phase properties?
It's a very strong questions, of course. For experimentals necessary to control condition our sample. But of course, you study the samples produced before us. It's produced by different method. It's nano diamond and micro diamond. After the graphitization process, it means the graphitization process controlled by temperature and heating and cooling time. And direct method to control of composition graphite and diamond, it's of course it's X-ray method, because it's possible to directly fix it line, crystalline line of graphite and crystalline line of diamond. And case of detonated sample, I show here. Two material produced from aniline and 1000 Celsius and here 2000. Let's see at the material produced at low temperatures has typical diamond lines, 3 diamond lines. And exist the amorphous not connected directly diamond.
Извините, у меня, по-видимому, какие-то проблемы со связью. Я даже себя на экране не вижу. Ну, извините, я уже надоел, наверное. Вот такая озвук я будет.
Excuse me, we can hear you. Would you so kind to switch off your microphone, please? Thank you.
And during the heating, the same materials, the disappear diamond line, it's only few, and appear refined lines here. And mean, in case of these materials, maybe completely sample is connected with graphite.
Okay, thank you.
And similar measurement was for micro-diamond that directly possible to observe transformation.
I
And
understand.
compare with thermoconductor heat capacity data, it's directly connected. And when the low temperature, in case of low temperature, the same materials, low temperature, it's usually a sample with low temperature, produce low temperature, has low temperature heat capacity. When the temperature aniline increased, the repetization concentration increased the heat capacity. It means the transformation from diamond to graphite increased the heat capacity, but it increased more higher than graphite. Let's see, it's after graphitization process, the sample has more higher heat capacity than crystalline graphite. It means that it's usually it's said graphite is turbostatic because it's graphite with different defects, not good packing, but it's layer materials, but not good crystals. In this case, heat capacity increased. But interesting is T-square temperature dependence. It's dependence like graphene, layer materials. Small interaction between layers. And this show directly and up to 2 Kelvin, up to 50 Kelvin. Is this a result? It's very interesting and new.
Okay, thank you. And one small question. Do you have plan about investigation doped diamonds?
I have also a question for our Professor Kripko, and also
I think it's possible to discuss in private.
Yes, I would like
thank
also
you.
to be involved in this discussion because I also have some small question about T-carbon loop system and the checking and control of it. Thank you very much again about very promising data presentation. And I think we can discuss during our pause a little bit later. And the next our speaker will be Dr. Lyudmila Borkovska from the Lashkarev Institute of Semiconductor Physics of the NAS of Ukraine. And she will present to us. Is she with? Yes. And a speaker will be co-author, researcher Yuri Seryoshkin. Yuri, are you with us? Yuri? The presentation would be about the laser acoustic method for the measurement, the nano oscillations of soil and the detecting of the buried objects. And it seems there is some technical problems, and we wait some couple of minutes, maybe something happens, because I can see that Yuri with us. So We have very limited time, so we can ask Professor Konstantin Nemchenko. Super. From the Azarian Kharkiv National University of Ukraine, and we kindly ask about presentation of his report about peculiarities of heat transfer of nanoconductors of different form and type of phonon boundary reflections. Please take your floor.
Thank you. Thank you. I'm glad to present to you our new results, maybe some review of our and some old results about the thermoconductivity now. We transition from the heat capacity of nanoconductors to the thermoconductivity of nanoconductors. Why we think that this situation is, this physics is very interesting, because in these nano devices, in these nanoconductors, that phonon transport that provides heat capacity and heat flow are enough interesting, and the situation in experiments and the theory are not clear until now. So we try to consider the very different, very different conductors with different cross sections, cylindrical one, rectangular one, and the nanowires with completely one-dimensional, and nano ribbons, each is completely nano two-dimensional substance. And together with this, we can consider the usual semiconductors and directives and enough high temperature, and even for the room temperature, in the case when the size of these conductors are too small. What does it mean? These conductors, sorry. What does it mean these conductors and its size and its dimensions are small? We means that in this case, the carriers of heat is the phonons without interaction between phonons. So these phonons can move from the source to the sink without interaction between them. So they can interact only with, for example, boundary of the structure, for the edge of the structure in the case of two-dimensional nanoribbons. And you may remember such a model, and we, all of us, take the theoretical problems. Firstly considered almost 100 years ago. It's so-called Knudsen regime in the rarefied gas. Maybe 100 years ago, they considered so-called rarefied gas in the tube with cylindrical cross-section or rectangular cross-section, and construct some theories known like a Knudsen series or Knudsen model. When we create pressure on the one side of the pipe and another pressure on the another side of the pipe, and we create the flow of the particles through the pipe. And in this case, of course, we can create this pressure gradient only in the, we have interaction of particle with the boundary of the space. And more frequently, we consider this interaction to be completely diffusive. What does it mean, completely diffusive? It means that when particle fall to the, or incident to the boundary or to the wall, they reflect uniformly in all directions. This idea was used again 100 years ago by Casimir, and he proposed to use this idea to describe phonon in solids, in the usual crystal, to describe the thermal conductivity of very long conductors. And in the case when we apply temperature gradient to the conductors along the conductor temperature gradient, they use the idea of Knudsen, of course, and get formula for the well-known formula for the thermal conductivity of the thermal conductors in the at the very enough low temperature or enough low sizes at the room temperature. But this theory was no, not theory, but this formula was created only in the case when we applied temperature gradient. But in reality, experimentators make another situation. They get the sub-sample of definite length, of finite length, and they get the heater from the one side of this sample, and the cooler from the other side of the sample. Oh, sorry. Sorry. So we can take heat in the one side of the sample and the coolant in another side of the sample and study the creation of the gradient and temperature inside this conductor. Over here. But this theory was created not 100 years ago, but 18, almost 100 years ago by Clausing and Smoluchowski. The well-known, especially Smoluchowski, maybe well-known to you and for us. Clausing and Smoluchowski have written an integral equation that take into account the motion of phonons from the heater. Again, sorry. They have written an integral equation that take into account motion of the phonons from the heater. For example, first term in the initial equation from the cooler inside the conductor, the second term, and the main term, the term that describes phonons, that goes from another boundary point to this boundary point. To simplify this equation, they renormalize the energy flux of this particle or simple flux of the particle, and by this third equation, and get the very simple integral equation and try to solve it for the simple gas, for the simple classical gas, in the cylindrical case and in the rectangular case. And they get numerical solution. I don't know how they did it 80 years ago. This integral equation is a Fredholm equation of the second type, and it needs some efforts to solve it exactly. But they did it and get some solution. I'll talk about it in the next slide. In this slide, I represent the new situation which appeared maybe 10 or 20 years ago when we started to study nanomaterials, and especially two-dimensional nanomaterials like nanoribbons. For example, we can present here some already classical experiment where they experimentators measure the thermal conductivity of these devices, of this structure. Over here, we can see the great number of narrow nanoribbons from the red heater to the almost green cooler over here. And in the picture on the right, you can see great quantity of very, very short nanowires, nano ribbons between the red heater and the green and not green. Oh, here the blue cooler. In these experiments we discussed below in the finish of my report. This integral equation can be solved, and the main relation that can be found in the linear dependence of temperature inside this conductor. You can present this, you can see these results on the figure in the slide. This is line for the different ratio between the length of conductor and the width of conductor. So, but in all cases, you can see almost linear dependence. You can use this idea that the final answer is linear and look for answer in this type. So you can answer in the form of linear dependence where the coefficient of factor delta t is a known value. This value can be found directly from the integral equation if you will insist that this equation should give the same results with the ends of conductor. So you will, in this case, get the direct correct answer for the maximum difference of temperature inside the conductor. This difference differ from the difference between heater and cooler, because phonons don't interact one with another, and can be even disappeared. We can discuss later why this difference can be disappeared. So the most interesting for us case is a two-dimensional case, because we can give the results which will strictly different from the results for cylindrical conductors or for rectangular, for example, nanowires. And these results will be valid for the two-dimensional nanoribbons. Over here, we present this simplified integral equation, because in two-dimensional case, these are really simplified. You can see the kernel H of this integral equation and the inhomogeneity G. You see that it's enough simple formula, you can integrate it, but unfortunately, this integral equation again can be solved directly, analytically. but we can solve it approximately by linear dependence, and found the real explicit value for the difference delta phi, where phi is the energy flux in each point of this two-dimensional nanoribbon. Over here, we can see that the results of this simple linear dependence are very just nice, corresponds to the results of numerical calculation of this integral equation. These results for the temperature gradient inside the sample make it allowed to get the heat flow, or maybe heat flux, or maybe coefficient of thermal conductivity inside this material, and compare with experimental data. Over here, we again present the point which reflects the numerical calculation and the formula for the enough simple formula that gives the linear dependence of the heat capacitance. Just for interesting, I should present the results with which at first were considered were obtained 10 years ago, but Clausing for the usual classical gas. They get this integral equation for the cylindrical tube. You can see this equation, integral equation, with the inhomogeneity, more complicated formula. Also, this formula more complicated. In this case, we can propose also new solution for linear results. Over here, we get some idea that was presented by Klaus and Hans Molokhovsky, but for cylindrical case, and get the explicit formula for the temperature dependence. Over here, we can see that dependence very nice coincide. No more than half of % they coincide in the two long conductors when the width to the length almost 100 on the left. The coincidence of integral equation and the results of the integral equation and analytical data. In this case, we can calculate directly and get explicit formula for the thermal heat flux and also thermal conductivity, because it is a normalized thermal conductivity coefficient, no, more exactly thermal conductance coefficient, surely, and compare it with the well-known results of the Knudsen in the cylindrical tube. These well-known results that we, all of us know these results, all of us knew, sorry, presented here by the dotted dashed lines. And we see that this idea that results of Knudsen regime or Casimir regime is valid for the long conductor, is valid, but not so exactly as we expected. The difference remains almost 14%, even for the conductors with the ratio length to diameter 100. Sorry. The results allow to generalize our results for the case of not only diffusion spectrum scattering on the boundary, but it's not so interesting like I want to discuss, excuse me. And here we can present the so-called rectangular shape and compare this equation with the result of Smolokhovsky first obtained 100 again years ago. But here we again get these results and show that we can get the explicit formula. But in this situation, it's not so nice because this formula is too big, and we even don't present it in this slide. In this slide, we can see the inhomogeneity H and the kernel G. And I can say that we can derive the final result, but these results are not, we can even present it in one slide. No, maybe next time we do it. So we can go back to our most interesting results for the nanowires, for the nanophysics, because here we present the results for the nano ribbons to experiment that is well known and B is not explained finally until now. The first experiment is the dependence of the width of the nano ribbons for different lengths and different temperature. It's not, I think, good described as well as we expected by the theory. But the following experiment, next experiment are very interesting because we don't know what to do with them. We take our simple model, you can see our formula 5 slides ago, and this formula very unexpectedly, it suspiciously describes the experimental data. And in this case, we can't say that our theory is too good because it's too nice description. So in this case, we should again and again try to find physical mechanisms that define thermal conductivity of this thermal.
I'm sorry, Professor Demchenko, we have just
so in this case, we
couple
should do
minutes
it
more,
and say the main summary of our paper that in any case, this question answered by the solution of the problem heat flow due to photons case should be solved again and should be discussed with the experimental and theoretician. Thank you.
Thank you again for very informative and important contribution. And I would like to ask our participants about a question, and it will be possible short question. Please.
You calculate the process in a picture of a ballistic regime. And when you compare data, it means the ballistic regime at very, very low temperature of good materials opposite. And you compare with graphene material, with experiment data at enough high temperature.
300 and 200.
Yes, it's enough high. Why? Too high. No, it's confusion or not?
Yes, I understand. It is the main reason of conclusion because we have enough room temperature, approximately room temperature, 200 Kelvin, 300 Kelvin. It is this temperature photon interact with one another. In this temperature, we have unclap processes. In this temperature, we can't say this, it is ballistic regime. But when we can use this formula for the pure ballistic regime, we get nice results and no other expression, theory can't explain this formula and we know what to do. Because in this case, something wrong happens, wrong with our physical understanding of what happens here. And we try to, that's why we present these results for you. And so we, right now, we don't know to do nothing except we are going to continue our studies this system. Thank you.
Thank you again. The next our speaker will be Dr. Andrei Sharikov from the Lashkarev Institute of Semiconductor Physics of the NAS of Ukraine. With the report stable partial dislocation, complexes in Varsel, Gali, and bimolecular dynamics and first principle simulations.
Good morning, ladies and gentlemen. I'm sorry, I have to correct. I'm not Sharikov, but Sarikov.
Good, and please take your floor.
Excuse me, am I good to hear?
Yes. Yes.
Okay. Thank you for giving me an opportunity to present this talk. And I have to correct, I think it's important. I'm not Sharikov, but Sarikov. And let me begin my talk. Stable partial dislocation complexes in Wurtzit, Gali, and bimolecular dynamics and first principle simulations. The motivation of this talk, excuse me, the motivation of this talk is defined, first of all, that gallium nitride is a wide band gap semiconductor material that is widely used in terahertz radiation devices. What is required for these devices is a careful control of electric properties, in particular the lifetime of charge carriers. Unlike many different other systems, the lifetime of charge carriers should not be increased, but reduced to ensure a proper functionality of these devices, but reduce it in a controlled way. And one may think about introduction of recombination centers targeted introduction of recombination centers in this material that could be used just to control to reduction in to reduce in a controlled way the lifetime of charge carriers for design applications. Our research was motivated and inspired by our previous experience with cubic silicon carbide, where Shockley partial dislocation complexes are known to be recombination centers introducing the energy states, the states in the band gap of this material. And similarity of cubic silicon carbide and gallium nitride is that these both materials do not have perfect substrate for deposition of layers, so that they contain large number of extended defects, so that, okay, we have thought about why not to try testing extended defect complexes, in particular partial dislocation complexes in gallium, and as possible modifier of the lifetime of charge carriers if they exist, first of all, and if they introduce the energy levels in the band gap. So the scope of this work encompasses identification of the atomic configuration of stable Shockley partial dislocation complexes located in basal planes of Wurtz Gallium. I stress this point that in this work we do not consider threading dislocations, we consider the dislocations and only part of them located in the basal planes of Wurtz Gallium. And identification of those levels, those modifications to the energy structure that is introduced by presence of these complexes. The methods we used were classical molecular dynamics simulations to track the interaction pathways of these the dislocations and complexes. Visualization and analysis of the structure of crystal structure of the material with these complexes, and density functional theory calculations and generalized gradient approximations to reveal the band structure. Okay, this slide shows atomic structure of versus gallium in a certain orientation, as shown here in the left part of this slide. The basal planes are perpendicular to the 3 × 1 direction, and exactly here the dislocations will be inserted that will be studied. And what we studied, I would like to notice that there are many possible variants of arrangement of dislocations in basal planes, but their interaction is a big and interesting topic, and it cannot be covered here in its entireness. Therefore, I will discuss only the formation of stable dislocation complex and their properties, leaving aside other kinds of interaction of dislocations, repulsive interaction, formation of complexes, and so on. So we introduced the 30-30 partial dislocations in 2 consecutive basal planes. 30 degrees Shockley partial dislocations with the cores are shown here. These are silicon core and carbon core. And in each plane, the dislocations together have 0 Burgers vectors, and in consecutive planes on the one side, they had 0 Burgers vectors together at all. Under these conditions, the interaction between them, attractive interaction between them, is expected. Such insertion of dislocations necessarily gave birth to the stacking folds between them. Another configuration was insertion in the same manner, insertion of 90 degrees Shockley partial dislocations. I mean, the Burgers vector is at the 90 degrees, with respect to the dislocation line. Again, we have silicon core and carbon core dislocations, and actually this picture repeats the previous one. This slide shows the interaction between 30 degrees dislocations, and we can see that they attract each to other very quickly, forming dislocation complexes with zero Burgers vectors, as shown here. The configurations of these complexes that can be called from our previous experience with other materials, we call it butterfly-like and flower-like dislocation complexes. And simulated annealing of such structure reveals that nothing happens with these complexes during annealing. Nothing means that neither they change their position, so they are motionless, nor they change their structure. Configuration remains the same. The same happens with 90 degrees dislocation. Their interactions producing the dislocation complexes of the configurations shown in the lower part of this slide. We have revealed the configurations of stable dislocation complexes. If they have, if they introduce the levels in the band gap, they can be considered as modifier of the lifetime of charge carriers in gallium N. Okay, the DFT calculations present the following modifications of the band structure of gallium N when the partial dislocation complexes are present. So here we have defect-free gallium, and the band gap, direct band gap of about 3.4 electron volts is clearly revealed. And the band structures of the materials of the cells with dislocation complexes 30 degrees and 90 degrees dislocation complexes. And we can see that they both complex types, or 4 complex types, because either 30 or 90 have 2 types of configurations, atomic configurations. They introduce levels in the band gap. Less levels and more distant from the conduction band, valence band top in the case of 30 partial dislocation complexes, and more levels closer to the valence band top in the case of 90 degrees dislocation complexes. Here, the wave functions of the defect zone maximum and minimum are shown. So different colors mean highest unoccupied molecular orbitals and lowest highest occupied and lowest unoccupied molecular orbitals. I would like to draw your attention. These are results of DFT calculations, and prior to performing the calculations of the energy structure of the cells, optimization of geometry has been performed, and see the modifications, some modifications of the atomic configuration of defects, especially this defect complex, as compared to molecular dynamic simulations. So this should be considered as more exact atomic configuration. And we can see that in the case of 30 dislocation complex, 30 degrees dislocation complexes, both maximum and minimum of defect zones are located on the same complex. While in the case of 90 degrees dislocation complexes, they are separated. We cannot consider the dislocation complexes apart, so there is some certain interaction between them, but these are limitations of the DFT, modern methods of DFT calculations and modern computer implementations, so that only pairs of such complexes must be studied. Here, the partial dislocation states along the x directions are shown for defect-free gallium, and no surprises, band gap free of any levels. Gallium N with 30-30 partial dislocation complexes, and we can see the rate distribution of electrons between the states takes place mainly at the flower-like complex, and the partial density of states peak is also observed here. I don't know if it's seen or not. It's encircled. It is situated at about 0.1 electron volt above the valence band top. In the case of 90 degrees partial dislocation complexes, I have to notice as well that some perturbations are introduced by the complexes in the conduction band and valence band of the material, but it has at least weaker effect on the recombination of charge carriers, which we're actually interested in. The same or perturbations are also observed in the case of 90 degrees partial dislocation complexes, and more pronounced partial density of states are observed in the band gap of this material. Here, the calculated absorption spectra of the cells of intact or initial gallium and gallium N with 30 degrees and 90 degrees complexes are shown. We can see that introduction of complexes shifts the fundamental edge of the absorption towards about, well, let's say about 0.1, 0.2 electron volts toward lower energies, as well as introduces absorption bands in the low energy part of the spectrum. To conclude this work, I have to say that we have found out stable dislocation complexes, their atomic configurations, and the dislocation complexes in the basal planes consisting of 30, 30, and 90, 90 degrees shortly partial dislocations with total zero Burgers vectors are stable. We have found more exact configurations, atomic configuration of these complexes, and these complexes have been shown to introduce energy levels in the band gap of gallium N, so that they may be considered to use as modifiers of the lifetime of charge carriers of this material for terahertz device applications. I would like to thank you for attention, and I would also like to thank Alexander Volhunvud Foundation for supporting this work in the framework of the Digital Cooperation Fellowship for Alumni in Ukraine program. Thank you for attention.
Thank you very much for perfect performed presentation. And now we have time for question. Is awesome question in our auditorium? Maybe everything was clear. Thank you again for contribution. And the next our speaker will be Professor Natalia Kizilova from the Khazarin Kharkiv National University of Ukraine.
Yeah, good morning. Good morning. I'll start.
Yes, yes, please take your time, take your flow.
Okay, so now I think it's visible. So my talk is about some interesting results, how to, based on the thermodynamic approach, how to construct the roughness on the surfaces of the coatings to produce some super physical properties for them. And it is some outline of my presentation, so I'll start with motivation, then some examples from nature-inspired coatings, and then experimental data, theoretical approach, and as usual, result discussions and conclusions and perspectives. So we know that now we have a large arsenal of different materials, so we can play with materials with different properties at nanoscale, different methods of preparation of these coatings, and also we can play with geometry. So we can produce some samples and make experiments, and what are the super properties. So we can start with some material with, to say, some hydrophilic or hydrophobic properties, but our aim to make them super, so super hydrophilic or super hydrophobic properties, or super oleophobic, oleophilic, or maybe it is anti-icing or icephobic. Icephobicity is also very important for different technical applications. So how to produce them? And also, of course, there are some inspirations from nature, there are some inspirations from our practice, from engineering practice, but you see, the way is time-consuming, this way is material-consuming, it is quite expensive to produce prototypes, to test them, and to understand that they are not super, not such super like we wanted before. So this is the idea, so whether we can use some theoretical approach to guess, not to guess, but to show which parameters could be better, what type of roughness. And last experiment shown that very interesting properties, super properties, is based on pillar type geometry. So how to produce this pillar type roughness. And also what chemical composition to add maybe to the tips of these pillars or maybe to the surface. So to produce these super properties. So we need a simple and robust approach that can will allow us to avoid the time and material consuming procedures for experiments, but starting with some ideas tested from the most general theory, which is thermodynamics. So starting from maybe 20 some years ago, it was really quite a boost in literature in studying the self-cleaning properties of the lotus leaf. So lotus leaf is always clean, and it was shown amazingly, it was shown that its clean properties is not based on the super smooth surface, but it is vice versa, it is super rough. So when we magnify the surface, we can see this microscale roughness, and also there are some nanoscale smaller roughness over these tips of this roughness. So then different types of surfaces of nature, from animals, from plants, were studied during the last decades. And for instance, a few examples, so there are plenty of them. One of them is butterfly wing, for instance. It is the macroscale. And you see it is not smooth, but the scales covering these wings, they are based, they are made of some nanostructures. So they are along this type of coating, and then also some perpendicular lines. And when we consider this wettability of this surface, you see it is the small droplet of water, and the contact angle is very close to 150. So it is very super hydrophobic, very super or ultra hydrophobic. There are different terms. So it is very interesting how to produce these super hydrophobic properties and icephobic also. So the water never freezes here. And also when you compare different types of coating and surfaces in nature, you see it is the lizard type. So it is famous lizard leg or fingers. They are covered with also nanostructures, and they can walk over all of the walls, even glass walls, and on the ceiling. And also the solution you see is different type of roughness, different type, but also pillar type roughness. And for instance, this freaky example, it is Salvinia, it is tropical plant. it can accumulate gas or air during tropical waterfalls. So when it is covered by water, so there's no access to oxygen, so the oxygen is inside, so air is captured here by these trichomes. So this is also looking like pillar type, but pillars are very, very complex structure. And it's interesting, they are nanoscale structure, but they are hydrophobic. They are covered by wax, so wax from nanocrystals. But the tip of this crown, it is hydrophilic point. So that's why this leaf could attach water over it, but accumulate oxygen to be weeks, days, and even weeks below the water and having oxygen for breathing. So it's very interesting. So solution from nature conferred by many different types of coating. It is pillar type structure, nanoscale, covered with some microscale, covered by some nanoscale materials. So what combinations of them? You know, we have dozens of materials, dozens of type of treatment of these materials, and also different types of geometries, hundreds. So the number of combinations is really terrible. So that's why we need some theoretical approach how to start with, what are the most promising over them. And here, fortunately, there are some systematical study, experimental study. This is one published in 2019. They are based on the PDMS material. When the surface of PDMS is smooth, it depends on the smoothness, on type of treatment. So the contact angle with water will be something like 110, 20. So it is at the limit of hydrophobicity. But when we produce some pillar type structure, the angle surprisingly increase up to 160. It is over the close to the limit of the measurements, static angle measurements. So, and also these guys, this group, they did some experiments with types. You see, they tried different types of location of these pillars, so square or hexagonal, and they also played with the cross-sectional area, not area, but the shape. So they made combinations with you see square, hexagonal, square, and first letter it is pentagonal shape of this pillar, then hexagon, octagon, then circle and square. And two lines, it is line and waved line, so a little bit different. So they played with them and they found it is, you see this data arranged by this contact angle. So the highest angle, it is pentagonal, pentagon, square, and hexagon location, but shape is pentagon here, cross-sectional pentagon. So why it is here? Why it is so big difference? 156 and 150. So what is the secret? So also they did 9 years later, they published the similar results with more complicated shapes. You see, it's also microscale and the same material. And they tried different size of this pillar type, also this porous type. So also they found some differences. So how could we predict or confirm some modeling by their results or validate it by the experimental data and propose the approach for future, not to waste time with preparation of the samples, but to find theoretical based, the most advanced one. So they, of course, they started with the geometry. So it is the sample of the pattern. So all the surface, just repetition of it. It is one pattern. White is empty place, and gray is the pillar. So it is top view. So they did experiment with pillar type A over A. So on this gray location could be octagon or pentagon or circle or square. So, and it is square location and it is hexagonal, just shifted two of them, I shifted according to the first two. So then they used also, you see, this type of some corner type or gamma type. So also, so we can arrange this pattern is also, it is like cubic pattern, it is just repeated here. So we can compute some non-dimensional parameters because, you know, when we apply for some general approach, so we need non-dimensional parameters. So we introduced here what's called surface porosity. So it is, if you look at this pattern, so it is a ratio of the area of the white squares here, so empty space, divided by the total space. It is porosity in the meaning of typical porosity of any material, but we consider it to the coated, to the surface of this material. Then shape complexity, perimeter over the square root of the cross-sectional area. It is for the gray only, so it could be pentagon or circle, so they will be non-dimensional parameter describing this surface. Sometimes when you multiply by 2, it's called the hydraulic diameter. It is well known in fluid mechanics. Then also distance between the two pillars and divided by this its shape. So A over B is called packing factor. It is also non-parameter, non-dimensional. Then roughness. Roughness is the total area of all the top, bottom, and surface or lateral surface of the pillar type structure. And also aspect ratio. It is A over H of this pillar. And also they are not all independent, so only 3 or only 4 of them are independent. So we can use 4 of them as the basic parameters and estimate some theoretical functions based on these 4 non-dimensional parameters. The most important thing to describe the super hydrophobicity or hydrophilicity, it is the surface energy. This energy is described by the free energy which is needed, or work that could be applied to material to create a new interface, a new surface. So this definition was done by Gibbs, and now it is they modified and to different materials, but the basic is here. So when we have 3-phase system, so solid support, then we have the liquid droplet. It could be oil or water, and we have the air or vapor outside this droplet. So we have 3 different phases. So then we have solid, vapor, and L liquid. So gamma is the surface tension between solid and vapor. It is here. Surface tension between liquid and vapor. It is what we call usually surface tension, the most important one when you have liquid droplets in the air, in the weightless conditions, for instance. And solid liquid, it is here. So interaction between the molecules of the solid and liquid. Some of them are very low, like solid vapor, it is very low surface energy, but some of them are quite high, liquid vapor. So then we know the famous Thomas Young law when we know the contact angle as a function of this ratio of these 3 surface energies, surface tensions or surface energies. And also there is Young-Dupré equation that can determine the same work to create new surface as a function of the just liquid vapor, so here interface, a surface tension, and angle, contact angle. So when we know contact angle, we can estimate this energy. So this is the basic theory, but the problem is the surface energy is usually defined, and we have some tables in the physical books, textbooks, tables for surface energies, but they are measured only for smooth surface of this material. So also for PDMAs, also we know this parameter, but only for smooth. What is the surface energy for a rough material, for a rough surface? So there is approximation for definition of this surface energy done in 1936 by Wenzel. So he proposed when we have this rough surface, so we can introduce the parameter R, it is roughness. So roughness is the ratio of the total surface area of all the roughness, so top, bottom, and lateral, divided by only the projective surface area, so only the top of this roughness. Then the cosine of this contact angle will differ from the cosine of the smooth surface by this parameter. Later, another case was considered when this material is hydrophobic, so sometimes the water, for instance, doesn't penetrate inside and between the roughness. So it is called the Wenzel state. This is called the Casey-Baxter state. So then this Casey-Baxter cosine is the function of cosine between the water and solid, water and air, and their relative concentrations in the system. But what is the problem? For instance, we can easily invent the state when we have one type of roughness, pillar type. So it is A with, it is distance B and H. So when the roughness is, to say, constant R. Then we change a little bit, so make one of them, some pillars thinner, some thicker, then the roughness will be the same, but the state could be different. It could be in between Wenzel and Kasebaxt. Or, for instance, here we play with height and width. So all these three types have the same R, but angles are different. So this is the problem. The roughness is not so one parameter model. So that's why we introduce 4 independent parameters. And also the state depends on the type of roughness. When it is flat, it is one case. When it is sharp, it is another one, because sharp pins, they could penetrate inside the bubble, inside the water droplet or oil droplet, or it could be smooth. So also many different types of roughness and how to discuss them, to describe. One of the most general approach is based on the Gibbs energy. So Gibbs introduced the, it is free energy, it is thermodynamical potential. Hito introduced it, and in general, when we have some interfaces in this system, for instance, this is one type of roughness, micro pillar roughness with nano roughness over it. So there could be Kasebaxt state for both macro and nano. Or there could be some liquid and material when the Kasebaxt state exists for only nano roughness, but for the micro it is Wenzel state. Or Wenzel state for both type of roughness. So different types depending on material and liquid. So that's why we have different types of interaction between these surfaces, and not only surfaces, we have also perimeters here. So each roughness has its perimeter. So then the Gibbs energy is defined as its general definition, like some constant geometry independent, like pressure and volume, for instance. But when we have experiments with the same volume of liquid and the same volume of material, solid material, and pressure to say ambient pressure is constant, temperature constant, relative humidity is the same. So we have this constant geometry independent term. But what is geometry dependent? It is total surface area between the phases I and J, to say solid, vapor, vapor, liquid, liquid, solid. And there could be different types of solids. Microstructure could be one type of solid material, nano another type. So they will be different in areas and different surface tensions. Then linear, so perimeters and linear tension, and the points.
Do you hear me?
Yeah.
Excuse me, but you have...
Yeah, I'm finishing this last slides. So
Thank
based on this approach, we can minimize the Gibbs energy and find out the most optimal geometry. So we did lots of computations, only a few of them are presented. It is a slit per Wenzel state, slit per Kasebaxt state, and we found that these values depend only on non-dimensional parameters. So only 4 parameters, and these coefficients are the same for different types. So it is a general rule. And we can generalize the Laplace law. You see, it is typical Laplace law, when the radius, in this case, it is not spherical particle, but particle dependent on the roughness. And then we compare it to the experiment done with these two articles listed before, and we had a very good correspondence to what they found in the experiment. And those are some conclusions. So it's quite a nice and successful approach, and is very general. And now we are working on experiments to continue these studies, because when we compute the optimization problem, we have the solution in the non-dimensional parameters. So it is not a unique solution. So different types of geometries could be with the same non-dimensional parameters. Thank you.
Thank you very much for presenting very promising and practical important results. And now we have a couple of minutes for question. Please, if have some question about this topic, about this presentation. So everything very clear.
Thank you.
Yes, thank you again for contribution. And our next speaker will be Professor Oksana Koplak from the Polytechnic University of Milan, Italy. Hello, Oksana.
Yes, hello, dear colleagues.
You're here with us. Please
yes.
take your floor.
Thank you very much. Can you... Can you see my presentation?
Yes. No, not yet, just you.
Let's try again.
You can see.
And now?
Yes, yes. Everything good, you can start.
Yes, I'm really glad to be here and present our recent results. Today I will talk about samarium cobalt and some effect of deposition power and post-annealing on microstructure and magnetic properties of samarium cobalt thick film. So let's start. First of all, it doesn't move. Why? Sorry. I don't know why it doesn't move. Okay, it's moved. So first of all, the question is why rare earth transition metal alloys is very important. Everyone knows that these materials, alloys, can be applied for motors, some generators, etc. But today, the area of application of rare earth transition metal alloys, it's increased a lot. I would like to show that some our results that we applied this alloys for magnetic tweezers in form of microwires. Why it's very interesting and very important, very promising for biomedical application, because you can move biology object without any mechanical stress, just due to the gradient of magnetic field. So it's very interesting for future medical application. Another topic, it's magnetic refrigeration. Rare earth metals have a very huge value of magnetocaloric effect. For example, gadolinium, it's a leader of magnetocaloric element for application at room temperature. Also, rare earth metals and alloys with transition metals can be used as a local magnetic field source. For example, here we used microparticles of rare earth transition metal alloys for use like local magnetic field for switching, for controlling low relaxation in molecular magnets. So, and next step, next topic for promising application of this type of alloys, it's application in micro electromechanical systems, MEMS systems. And about this topic, I will talk today. So why it's interesting, why it's promising, why we can study, we should study, we studied this topic, because this approach to use the magnetic micromagnets consists in eliminating the need of electromagnets by using permanent magnets, small permanent magnets as a source of local magnetic field. And it's really interesting because these small micromagnets that deposited on the MEMS structures can provide tunability by simply adjusting the distance to the radio frequency part of the circuits. And here you can see schematically some scheme how it can be realized. And the second one, it's our prototype that we deposited, they create in our laboratory. The small pieces, quadratic one, it's a permanent magnet that the distance between them and wave-wide can be tuned in this MEMS system and to control propagation of spin wave in wave-wide. So we propose to use samarium cobalt for these small micromagnets. Why samarium cobalt? First of all, everybody knows that samarium cobalt is sintered permanent magnet, and fabrication steps are well known. So it consists some melting, crushing, milling, pressing, annealing, and also magnetizing. And each steps are optimized, maximally optimized. And at the end, we can have the very nice crystal structure with a very beautiful domain structure. Here you can see MFM image that was done by magnetic force microscope with the beautiful domains, grain domains also. It's around 20 microns, these domains, with high intensity. And this microstructure gives very high coercitivity. For example, at room temperature, it can be reached at around 2 Tesla. And you see this squared hysteresis loop present on the slide. And another very nice attractive properties like excellent temperature stability, high resistance to corrosion, and demagnetization. So, but the question is what we will have if we used some sputtering deposition. For example, RF sputtering. So there is a lot of technical questions, technical problems. It's some challenge because we have a lot of parameters that should be controlled, like deposition temperature, deposition power, level of vacuum, or deposition pressure, etc. So it's a lot of parameters that can be tuned during deposition or after, like annealing temperature. We create some heterostructures, samarium cobalt. It's a film with 500 nanometer thickness that was deposited by RF sputtering. We use tungsten as a buffer and copper layer. Why tungsten? Because tungsten is a beautiful metal to help to avoid degradation or oxidation. And we use silicon. Why silicon? Because it will be very easy to use the substrate for future application directly in MEMS device. And the idea was to find the parameters that should be controlled to increase the magnetic properties of our samarium cobalt film. We start with fabrication. Here you can see typical images of the fresh deposited heterostructures. You can see a beautiful interface between tungsten and samarium cobalt. The interface is very flat without interdiffusion. Also, we performed DX analysis to calculate the ratio between samarium and cobalt to check the phase composition. After that, and these heterostructures was deposited as at 300 watt at RF sputtering, RF power, which is equivalent to energy density of 66 milliwatt per millimeter squared. And also argon pressure, the value you can see some details on the slide. As I said, tungsten layer provide very good adhesion and prevent any oxidation or interdiffusion without delamination. This heterostructure was saved more than 1-2 years and without delamination, some degradation, so it was completely safe. And this film was amorphous because we deposited at room temperature. You can see that one intensity peak corresponds to tungsten and amorphous gallo corresponds to samarium cobalt. And also the hysteresis, it was very narrow, with very small coercitivity that can correspond to small nanocrystals that can form on the interface between tungsten and samarium cobalt. Also, we check this idea hypothesis by XPS analysis. You can see here cobalt 2p level and samarium 3d level that corresponds the main element in our film. So cobalt cations occupying octahedral and tetrahedral positions. That means that we have some mix of two phases. at the end. So, and also we check the effect of plasma cleaning. Here you can see three type of XRD spectra and three type of hysteresis that corresponds to different plasma cleaning in argon or in oxygen, and blue one it's without any plasma cleaning, and there is magnetic results was absolutely same, so there is no any effect of plasma cleaning on the magnetic properties of the film, so it's very negligible. But what is more interesting, more promising, it's post-annealing. So this amorphous film was annealed at high temperature. It's vacuum annealing, and here you can see some images, some microstructure evolution. So first of all, it was amorphous, absolutely homogeneous, but after 650 and 750 Celsius, we see the very nice crystal structure with grains around 60, 70 nanometers. And what is interesting with increasing the temperature, the distribution of grain size, it was more narrow. The size of grains it was bigger, but distribution was narrow. Its log normal distribution was observed, and it was repeatable also. This microstructural evolution also corresponds to the evolution of magnetic properties. In the right side of the slide, you can see a set of hysteresis that was measured in plane and out of plane orientation. Orange one, it's out of plane, blue one, it's in plane orientation, and we have also anisotropy, so it's in plane magnetization. Our films have in plane anisotropy, and you can see that squareness of this loop completely depends on the temperature of annealing. At 650, it's more squared. But coercitivity it's more higher at 750. So the short conclusion is, intermediate conclusion is that we can tune or residual magnetization or coercitivity due to the post annealing our film. And these small steps on the hysteresis loops, you see it's not so squared, let's say. You see several steps on the hysteresis loops that can correspond a mix of magnetic phases, and we confirm it by XRD analysis. There is a mix of two phases, samarium cobalt 5 and samarium 2 cobalt 17. And you can see also the peak position and some differences between three spectra before annealing and after annealing in different temperature, like 650, 750. But what is interesting, both of these phases has partial texturization. We perform some polar figure measurement, pole figure measurements. This beautiful square cycle corresponds, confirms the texturization of samarium cobalt 5 and samarium 2 cobalt 17 phase, but in preferential direction was 110 for samarium cobalt 5 and 300 for samarium 2 cobalt 17 phase. So it's also interesting because in this direction we can tune the texturization of our film by temperature. But for understand the interaction between these two phases, because there is also some intergrain coupling or coupling between different grains with different size, with different direction, we performed fork analysis. Fork analysis, it means first order curve or reversal curve analysis.
Sana, have you here just a couple of
Yeah, I will be faster. Sorry. Fork analysis, and here we can distinguish the interface coupling between two phases. If you are interested in these results, you can check this link. Is our article. It's more or less fresh, and here we describe this interaction and how we can check directly from this methodology, let's say. And another interesting effect that you observed is effect of deposition power. Here you can see some examples, XRD spectra for G type of samples that was deposited at different deposition power, 100, 200, and 300 watt. So, and you can see some evaluations, some changes between the ratio of these two phases that gives us the changes of the magnetic properties. You can see the form of the hysteresis loop, it's changed a lot versus due to the changes increasing of the deposition power. So, if we change the temperature of annealing, it doesn't change, it doesn't affect much, a lot of the magnetic properties of the film. So you can see 650 1/2 an hour and 1 hour, it's practically the same magnetic properties. So it's just some examples. I showed some examples how we can tune the magnetic properties of the samarium cobalt film in heterostructures by the change due to the deposition or post annealing. And for application, it's very promising these results, and we hope to apply it in MEMS structure, because it's a main idea of European project M&Ms. And I would like to thank you for your attention in this moment. And I would like to thank my co-authors and the people who touch this field of research. Thank you very much.
Thank you very much for sharing with us so perfect prepared and promising results. And now we have just a couple of minutes for question, please.
Hello, can you hear me?
Yeah.
Yeah, first of all, thank you very much for the inspiring talk. I have a small question, or rather a remark about the slide number 7,
Yes.
where the
Let's move.
spectrum was presented. Yeah, this one. So the thing is that our group are also involved in XPS, and from our experience, it is, I mean, here in the decomposition, it can be seen that the half widths of the peaks are very different for the two components of the 2P lines. You see that the one on the right is that there are very narrow peaks, and the one on the left they are quite broad. And from our experience, the reviewers in the journals often complain about such kind of decompositions, and just maybe it's kind of a little piece of advice, if you allow me. Thank you.
It's a beautiful remarks. So you are absolutely right. So because we also always have some mix of cobalt 2+ and cobalt 3+ plus oxidation states. Absolutely agree with your decomposition half and intensity. So it's these rules, it works. For our system, because it's thin film, so of course XPS, you know, it's very sensitive to the surface, and you always have some oxidation on the surface, on the because it's metal. Yes, I'm agree that it's very delicate, this analysis, but in our case the idea was the check the composition and the ratio between cobalt and samarium. So we didn't spend a lot of time for perfect decomposition of this ratio between cobalt 3+ or cobalt 2+ ions, because for our interesting it was the magnetic properties, so the composition between cobalt and samarium. and for that reason, I present this type of results. But I would like to thank you for these remarks, and I will take attention, of course. Thanks.
Thank you very much. Have a nice day.
Thank you a lot. Thank you for very interesting contribution. Yes, very important for us. And we would like to invite our next speaker, Professor Evgen Len, from the Kurdumov Institute for Metal Physics of the NAS of Ukraine.
Thanks a lot. Have a nice day.
Yes, thank you. Thank you very much. And the title of report of Professor Len will be low work function graphene posit nanostructures. Professor Len, are you with us? Are you able to listen to me?
Yes.
Are you hear me? Hear me?
Yes, I hear you.
Oh, super. Yeah. But we cannot to see you. Oh. Yes. Okay. We already can see the maybe middle part of your. So please let your flow. Take your flow.
Good afternoon. I'm pleased to present our work, and I hope that my English will not be a problem for communication. Today, I will present the results of theoretical studies that have been carried out in close collaboration between the Department of Electronic Structure and Electronic Property of the Kurdumov Institute, the Department of Applied Physics and Nanomaterials of the Kyiv Academic University, and the Group of Condensed Matter Theory of the University of Zurich. Because of time limitations, I will not discuss our experimental research on this topic, but I will only show our team. We investigate the work function of materials. I mean the energy that needs to be provided to the most energetic electrons in the system to move them away from the surface over a sufficiently large distance. In metals at 0 Kelvin, this will be the difference between the Fermi energy and the vacuum level. The effectiveness of catalysis, the thermal and photovoltaic energy conversion depends on the value of the work function. Work function play an important role in interface chemistry and electronic device design because it determines the energy band deformation at the interface between materials in electrical. Also, work function is the main characteristic of vacuum electronic devices. It determines their rise and energy effectiveness. For example, the emission current density in the cathodes of electron microscopes, ray tubes, plasma screens, and thermionic energy converters is directly determined by the work function, which is included in the exponent of the Richardson equation. Thus, the task of controlling the work function of various materials is a K1 for many modern areas of science and technology. So, what are the ways to implement such control? The first is associated with a change in the position of the Fermi level relative to the vacuum level. This can be obtained, for example, by changing the electron concentration due to doping or changing the electronic structure itself. For example, through position and deformation, including from defect. If a perpendicular to the surface external electric field is applied to the system, the Schottky effect reduces the highest and widest of potential barrier and correspondingly reduces the effective work function by value delta phi, which has zero dependence on the electric field strength. Second way, a similar result to the Schottky effect can be obtained due to creating a surface dipole moment, which generates its own electric field, which can increase or decrease the work function of the material. B and multi-layered graphene allows the synchronous application of both mechanisms of the function change. Firstly, it can be intercalated with atom, for example, alkali metals, which allows the mechanisms associated with the Fermi level shift. Secondly, the idea of polar atomic complexes, for example, alkali metal atoms, which can be fixed between the layers of bilayer graphene and reduce the work function due to the surface dipoles formation, has already been proposed in the literature. However, such studies have been carried out without investigating the work function or with incorrect assumptions about the nature of the atomic complexes formed on the graphene surface, as our initial calculations have shown. For our DFT calculation, we use the quantum espresso with the PB-Sol exchange correlation functional, the dipole compensation, and the van der Waals correction. Relaxation was performed for all structure. In nature, there are two types of bilayer graphene, AB and AA type, which differ in the relative arrangement of in layers. We will start with the more stable AB type. Its structure is shown on the left. One can see that the graphene layers are shifted relative to each other. The graphs on the right shows the value of potential averaged along the axis perpendicular to graphene planes. Along this direction, the unit cell is expanded to adequately reproduce the vacuum gap. Thus, the potential value at the cell boundary can be considered as the vacuum energy level. Then the difference between it and the Fermi level will determine the work function of the system. In this case, it is 4.33 electron volts, which relates well with the experimental data. In the case of AA type graphene, the graphene layers are arranged exactly under each other. The work function of this structure is lower than that of the AB type structure and is equal to 3.79 electron volts. Calculation also give a lower binding energy for this type of graphene. Intercalation with an alkali metal, in our case, lithium, at the maximum concentration of the intercalants should give the maximum change in the work function due to an increase in the electron concentration in the graphene layers and a corresponding shift of the Fermi level. However, for AB type graphene, the work function decrease only 0.01 electron volts. In the case of AA graphene, the maximum concentration of the intercoolant even leads to an increase in the work function by 0.1 electron volts compared to the unintercalated sample. This behavior is explained by the large deformation caused by cesium in the graphene lattice when it is located in each cell. At the same time, such a strain makes AA graphene more energetically favorable. Reducing the cesium concentration to 1 atom per 4 cells leads to a significant weakening of the lateral strain in A graphene and to 0.36 electron volt decrease in the work function compared to the poor material. By creating near surface dipoles of different orientations, it is possible to both decrease and increase the value of the work function. For example, the appearance of oxygen atoms, here they are red bullets. The appearance of oxygen atoms on the surface of cesium intercalated AA in the same amount the number of cesium atoms leads to a significant increase in the work function. The appearance of atomic complexes is the opposite dipole moment, such as oxygen cesium on the graphene surface due to adsorption. These atoms lead to a significant decrease in the work function down to 2.0 electron volts. The effect of defects, in particular vacancies, on the work function is also important. For example, in poor AB graphene, they lead to a significant increase in the work function. Sample. The same effect is observed for AA graphene. For both types of graphene, the work function is about 5 electron volts. In contrast to defect-free AB graphene, oxygen atoms decrease the work function because partially filling the vacancies. By adding cesium atoms to the oxygen, the work function can be reduced to 2.33 electron volts. The most interesting results obtained for cesium intercalated defect-free AB graphene with an oxygen cesium atomic complex on the surface. In addition to the lowest value of the work function, about 1.19 electron volts, we can see that the top cesium atoms is relatively close to the oxygen atom, and the oxygen atom itself is close to the one of the carbon atoms. That is in the contrast to the previous cases when oxygen cesium complexes formed typical van der Waals bonds. In this case, equivalent bonds is possible. I have presented my conclusion during the report. Thank you for your attention.
Thank you very much for very good time accuracy, and also your contribution is greatly appreciated. Do you have any question to the report? Maybe someone have? Yes?
Yes, can I ask?
Yes, yes, please.
So I would like to thanks for the very interesting presentation. And I know that you are a theoretician, but I have experimental question. So maybe you know, maybe you have some collaboration, the people who measure it directly as a work function, maybe by XPS, not XPS, it's a UPS, or directly by IFM, Kelvin probe. And did you observe, they maybe observed some differences in vacuum in air? It's a first part of question. And second part of question is, did you calculate, did you find some differences versus the number of layers of graphenes? Thanks.
Thank you. The first question, I know many works where measured work function, and in Ukraine, in Kyiv, there are 2 or maybe 3 places when we can measure work function. I don't know, do you need address of
No. The question is, so there are some differences between different type of measurements and your calculation, or you haven't?
I can send you big review on this term, and you can see who and how measured. And second question about
Would you repeat it, please?
Yes. Second question about calculation, theoretical calculation. Did you calculate? Did you observe the differences for monolayers, for several numbers of layers? Did you take into the account?
We now only started how calculation works, but probably we
maybe it will be better if
we measured and calculated Raman spectroscopy, and we see the differences between number of layer in graphene.
Thank you.
Thank you very much again for very important contribution, and to the Professor Len. And the next our speaker will be Dr. Viktor Kisluk from the Kurdumov Institute of Metal Physics of the NAS of Ukraine. Are you hear me?
Yeah, I hear you.
Yes, please take your phone.
Okay. Good afternoon, dear colleagues, Madam Chair. Thank you for introducing our presentation entitled Relationship between nanostructure of the ethylene vinyl acetate copolymer film and its creep lifetime under ultraviolet. I am Viktor Kisluk from Institute of Metal Physics of the NAS of Ukraine, and it's my pleasure to introduce my colleagues. This is the researchers from Institute of Metal Physics, Riiko Trechko, Ladislav Shevenyuk, and Yuri Palushkin, and also the team from Bordeaux University, Jean-Marc Olive and Gilles Pakistan. Prior to proceed, I would like to thanks to Ukrainian defenders, because due to their efforts, we can live and make research in free Ukraine. So, few words about the material itself. It consists of two copolymers. This is the correct name of this polymer, polyethylene covinyl acetate. It consists of polymers with polymer units of ethylene and vinyl acetate, which randomly redistributed along the whole copolymer, which is called EVA. It's a short name of this material. And its remarkable feature is the ability to adjust its rheological and mechanical properties to the required conditions. So it depends mainly on the vinyl acetate content, which can vary from 0 to 10%. And in our particular research, we are interested in the material used for lamination of photovoltaic encapsulants with vinyl acetate content corresponding to 28 weight percent, which is 11 mole percent. And this is the formula which associates these two notations. And you also can find many useful formula in our recent preprint by this link. Please enter, and there are many expressions which follows our research. So another feature of this material is the existence of nanoparticle-like segments, which is consisted of ethylene component. So the objective of our research is it concerns the EVA encapsulant lifetime, and so we plan to establish the relation between the microscopic physical phenomena, and namely the phenomena associated with mechanical properties of this material, and to construct a system of parameters which allows one to make quantitative characterization of the material, so it can be used for material rating. As always, there are a lot of materials appears which consist of not only pure polymers, but also the composite. And so this approach we expect will be useful for these researchers and all as well as producers. So another feature of this polymer is its viscoelastic rheological behavior. And so we may demonstrate it from the stress and strain curves. And you see the stress versus deformation. We see the very huge deformation range. The fracture proceeds at the end of this curve. So, and this material is delivered with in rolls. We use this material after curing. It also, in its delivered state, it contains the curing agent. And so we received the cured sample, but the curing, just annealing at enhanced temperature, does not reveal any reducing of this viscose component, and there's also the deformation is rather huge. So we propose the specific schema for creep experiment. Creep is the reaction of the material to the constant load. We apply the constant load after some preparatory procedure. It consists of preloading the material. This is the first, the preloading, and the value of where we finish our preloading value. It explained in detail in our previous paper here, and just a few words. It only before the fracture of the material itself, and then after relaxation of the load, we applied load for creep. So load with the controllable load rate. And from the right-hand picture here, this figure corresponds to of these processes. The preloading, this is the preloading curve, which is described by right and below axis, and we stop at some fixed strain value, and the creep process. We see that after preloading, the material becomes mostly elastic, which is reflected by this linear dependence of the material stress versus strain. So we apply the model equations to describe this dependence, namely the time of creep, and we relate this time of creep to the activation energy of the process. This is the model equations, which is used on the basis of Zhurkov equations, where this activation energy is linear dependent on the stress. This is the external stress. And Kauzmann-Eyring equation, which is well known, based on the Morse potential of the critical event. A critical event is the local formation of some cavity or bone breaking, and it can be described by the energy profile of the points corresponding to the formation of local rupture. And this profile has its activation energy, and actually this activation energy will be reduced after applying the external load, as some energy will be some work will be done by external energy, and this work also determine the reduction of the activation energy. So the experiment we use here the typical kinetics, and at any added value of force applied during the creep, we see that the behavior drastically dependent on the radiation. At the absence of radiation, we have much longer period of creep till the fracture here. And when we apply the monochromatic ultraviolet radiation from light-emitting diode with 365 nanometers, the time is drastically reduced. And also we see that at the beginning of these kinetics, it almost the same as the dark kinetics of the sample, non-radiated. And it means that the fluctuations which brings the additional energy to initiate the critical event of rupture just wait when the sufficient energy is accumulated due to energy absorption from ultraviolet. And we expect that this energy absorbed from a chromophoric group of double bonding of acetate side group. So the dependence of time versus stress, we see two linear dependence, two segments, and the part corresponding to irradiated sample has rather lower value of lifetime of creep. So parameters derived based on the above models are also demonstrative of the nature of the critical events of the initial rupture and local site of the polymer, and in particular the activation energy calculated on the basis of derived parameters from phenomenological equations of Jurkov and Kazman Eyring, approximately very close, and they are several times lower than actual energy of covalent bonding between carbon-carbon interaction. So we may conclude that the critical event proceeds via the sleeping of adjacent chains rather than covalent bond breaking. There are also another important parameters we used, for instance, the surface energy density, which is in good consistency with Griffith's criterion for the crack propagation. So to transfer the external stress, we need some mechanism how this external stress, which we applied to grips, this is the experimental setup, grips which capture the sample and then moves in opposite directions. So how this stress transfers to the local size. So we may suppose that this happens due to existence of nanocrystalline particles whose presence here is confirmed by X-ray diffraction patterns. And we may calculate, due to Scherrer equation, the typical size of these particles. But this size is much lower than the size we see at the fractograms and scanning electron microscope. And here we see the size of samples of the order of 1 to 10 microns. So differential scanning calorimetry curves demonstrate also the existence of melting of crystals and the existence of formation of curing as exothermic process. And also during the cooling, the reverse process of crystallizations also evidently appeared. So to find out the nature of these huge particles, which is much higher than the calculated from Scherrer formula, we proceed the simultaneous in situ experiment of atomic force microscopy and directly in differential scanning calorimeter. So we see the formation of these huge particles starts prior in huge and approximately 2 hours prior to the formation of the crystals, which is shown on the coarse quantitative, shown in the differential scanning calorimetry. So we may conclude that this happens probably due to a huge temperature gradient, or probably these particles has another nature than nanoparticles inside the volume, because this technique, atomic force microscopy, is rather surface oriented. So the conclusion, we found that the creep of lifetime versus creep force dependence is effective indicator to monitor the bonds responsible. We propose the scheme how to derive these parameters, and we see that from this experiment can surely confirm that the critical event of foil rupture is associated with slipping of adjacent polymer chains. And also, for the first time, it was discovered some clusters of micron size, and presumably they are formed under high temperature gradient. So thank you for your attention, and I should acknowledge the support by National Academy of Sciences and also the participation of our colleagues who made supplementary measurements and discussed with us the results. So thank you for your attention, and also I just remind that today is the day of National Flag of Ukraine. So congratulations to all Ukrainians and to those who supports and stands with Ukraine. Thank you.
Thank you very much for the presentation. Do we have any question? No question yet, so thanks once again. According to the program, we have a coffee break now, but we a little bit shifted in time. So if anybody needs to have some hot drink, please do it, but we will continue. And the next speaker will be Dr. Anastasia Solomonenko from the Gurdimov Institute of Metal Physics of NASH of Ukraine. Dr. Solomonenko, are you with us?
Yeah. Can you hear me?
Yes, I can hear.
I can't share my presentation. Why?
I don't know. What do you see? Please press share screen and then choose your presentation.
I can share. This not active share. It's gray, not green.
Wow. Okay. I think that we can switch you with another speaker, and while we do this,
Alt plus S.
what?
Alt plus S. It's short.
Please try to do as recommend participants Korotko.
No.
Not working. Okay, please send your presentation to our conference mail. We will download it and give you a floor after the next speaker, okay?
Okay.
Okay, then I invite the PhD student Denis Mazar from the Lashkaryov Institute of Semiconductor Physics of NASA of Ukraine. Denis?
Yes, I am here.
Can you share your screen?
Now I share screen. One moment, please. Share screen. Share.
Okay.
You see my presentation?
Yes, I can see it. Please start.
1 minute. You can see the next slide. Or you see the first slide?
No, I can see the second slide.
Okay. All is good. Okay, I am starter now.
Yes, please start.
Dear participants and listeners of the conference, I am pleased to present a report in situ Raman and confocal FM microscopy of co-exciting insulation and metallic domains in vanadium dioxide film. The research was conducted at the Diagnostic Center of Lashkaryov Institute of Semiconductor Physics, National Academy of Sciences of Ukraine. The samples were studied using the triple spectrometer Horaiba GBON T6430 and infrared Fourier spectrometer Bruker Vertex 70V. and the scanning probe microscope Nanoscale CA. Polycrystalline vanadium dioxide film investigate in the work were grown in the Department of Ion Beam Engineering and Structural Analysis. The tin vanadium dioxide films were synthesized using magnetron sputtering on a substrate of high purity silicon, followed by annealing at 400 degrees Celsius for 20 minutes. Our study is significant as it aims to investigate a structural, optical, and electrical characteristics of vanadium dioxide film, which a focus of understanding the metal insulation phase transition near the critical temperature on the nanoscale. In this work, we investigate in detail the local subnanometer distribution of different structural phases around the metal insulation transition and thermal and voltage triggered structural change of epitaxial vanadium dioxide tin films. In today's electronics, the transition to the nanoscale is critical. It enables higher speed, efficiency, and functionality, while reducing energy consumption and cost. Therefore, research at the nanoscale is a vital task. Vanadium oxides with various crystallite structure offer unique electrical, optical, optoelectronic, and magnetic properties, which could be manipulated for various applications such as energy conversion storage device and supercapacitor, memristor, uncooled bolometers, smart thermochromic coating, and more. Unique properties include a sharp and reversible metal insulation fast transition near room temperature. The fast transition process is ultra-fast, hundreds of femtoseconds. The fast transition involved a significant change in resistivity, more than 5 orders of magnitude, and infrared optical reflection transmission, 2 orders of magnitude. The parameters of plane transition is vanadium dioxide film depend on the strain, doping, defect concentration, and grain. However, in real world device structure utilizing polycrystalline vanadium dioxide film, the parameter of the fast transition can vary significantly due to the special homogeneity in structural and electronic properties, and the result impact on the dynamics of the metal insulation transition. Special fast homogeneity is a primary upscale to understanding to the mechanism of fast transition. Fast segregation can arise due to the inevitable unit and the local distribution of stress or chemical composition with the sample. For more, most spectroscopy method average data across several crystallized with the resolution limit without accounting of significant variation in the size and deformation of individual nanograins, which lead to the emergence of mixture of different competing structural phases. For example, M1, M2, rutil, under identical extensional condition. Infrared Fourier spectrometry was used to investigate the microscopic optical properties of the vanadium dioxide film. In the first image, you can see a reflection spectra obtained by heating from the 300 to 366 Kelvin. With gradual heating to the fast transition temperature, the reflection coefficient changed very little. As the critical temperature approached, there is a sharp increase which stops after suppressing the critical temperature. Infrared spectra show that the reflection coefficient is the vanadium dioxide film in the near-infrared region exhibits a jump in transition and hysteresis during sequential heating and cooling. The critical temperature for the fast transition we found to be 347 and 340 Kelvin respectively. Raman spectroscopy is non-destructible and effective method for identifying the structural phase of vanadium oxide and investigation the spatial distribution of crystal structure, strain, and doping of films. Confocal Raman microscopy enables 3-dimensional mapping with a submicron resolution. According to group theoretical analysis, vanadium dioxide is expected to have several Raman active phonon modes. For monoclinic, M1 has 18 active modes, 9 Hg and 9 Bg modes. Tetragonal rutil has 4 active modes, A1G, B1G, B2G, and Ag. On this slide, you can see Raman spectra vanadium dioxide before the fast transition, spectrum A, and after, spectrum B. The Raman spectrum of the vanadium dioxide film measured at room temperature exhibits some phonon bands that correspond to Ag and Bg symmetry A. The two main phonon bands in the low frequency region of the spectrum at 192 and 223 centimeter relate to the tilting motion and pairing vanadification of the long vanadi-vanadi dimer. The vibrations are directly perpendicular and along the CR axis respectively. The band of 388 centimeter correspond to valence vibration vanadification in the short vanadi-vanadi dimer. All the rest of the phonon bands are assigned to vibration of vanadi oxygen bonds. The strongest phonon bond with a maximum at 618 centimeter correspond to the vanadi oxygen bond, stretching vibration as they usually used at an identified of structural phase of vanadium dioxide. On this slide, you can see micro-Raman spectra obtained over a temperature range from 78 to 353 Kelvin. Analysis of the temperature depends on the characteristic frequencies of vanadi-vanadi and vanadi oxygen bonds showed a non-monotonic change. For each characteristic band, a hysteresis loop was constructed and critical fast transition temperature was determined, which nearly coincides. In the temperature range from 388 to 344 Kelvin, a decrease in the intensity of phonon bands is observed, which may be due to the coincidence of particle transforming or two structural phases. This prompts us to investigate this narrow temperature range more thoroughly, including the spatial distribution of this phase of temperature close to the critical point. The confocal Raman spectroscopy with submicron resolution was implemented to provide information of the spatial distribution of monoclinic and rutil phase during the MIT metal insulation transition below a few degrees of critical temperature. In this slide, you can see a Raman 2 and 2 micron map of the thermal evolution of structural phase of vanadium dioxide film. At room temperature, the first map shows a nearly homogeneous array of blue pixels corresponding to the monoclinic phase with almost uniform intensity, indication spatial homogeneity of M1 phase through the vanadium dioxide film. As the temperature approaches the fast transition, micrometer size domain, red pixels, corresponding to the rutil phase, appears in the map. When the temperature is raised to 67 degrees Celsius, the metallic domains of the rutil phase grow, and the map predominantly shows the red pixels. It's the next in front map. Upon reaching 70 degrees Celsius, the map contains only red pixel, indication a completely structural transformation with semiconductor and metallic phase. In addition to Raman studies, we demonstrate the coexistence of two structural phases approaching the critical temperature of the fast transition, but did not allow for pressure identification of the fast nucleon site. Investigation of the distribution of electrical properties at the fast transition and the nanoscale were conducted. The SSRM method allows simulating measurements of the sample's topography and its electrical parameters at the specific point at low bias, and emergence of the metallic rutil phase occurs within large grains. With increasing bias, the process spread through the grain, then to smaller grains, until all nanocrystallites become conductive. Cross-section of resistance maps show the resistance difference between grains and grain boundaries is 1 to 2 orders of magnitude at low bias. At a bias of the 3 volts, phase resistance fluctuation amount to only plus minus half kilo ohms. The next graph shows the resistance difference between grains and grain boundaries at two temperatures: room temperature, 26 degrees Celsius, and a temperature close to the phase transition, 45 degrees Celsius. In summary, our research indicates that the smaller scale of phase segregation and the lack of construction phase visualization mechanism at the nanoscale make it extremely challenging to obtain a distribution of structural phase in real space with high spatial resolution. The data obtained are critical for understanding how the structural transition process occurs and how various factors such as crystallized size, grain boundaries, and their defects are deformation states determine the material's properties. This all. Thank you for your attention.
Thank you very much for your interesting presentation. And now we have the time for question. Please. Somebody can give a microphone to our participant.
Can I ask?
Moment, we
Yeah.
have
Okay.
first in a conference hall, and you will.
First of all, thank you for your presentation, and my questions about slide 4, where you deconvolute Raman's spectra and peaks very different in the width. Can you explain physics that's staying behind?
You want to slide 4? Yes. I one moment. Slide 4. You want this slide or?
Yes.
Yes, and can you repeat the question?
In the Raman spectra, you deconvoluted it, yeah, and widths of the peaks really different between them. Can you explain physics that stays behind this difference?
In this spectra, we see 18 phonon modes. Phonon modes AG it's a vanadium tilting, and other 6 it's a vanadium oxygen tilting. When Raman
Oh, I'm asking about lava spectra.
The second B.
Yes, widths of bands very different, and I'm interested in physics that stand behind it.
Yes, when we have a structural transition, the structure of vanadium oxide is rebuilt. When rebuilt structure, we have a new tilting, and this new tilting have more very low and very very low intensity. But if we write more time, we can see some
it will be better if our participants, if this question we send in chat, we will send, and we will have a little bit more time for make it clear. Yes, and we have a couple of minutes for the second question. If is it not long, or we can, if it need time, we can also to write it in chat. Denise, Denise, is everything okay? You are with us?
Yes, yes, I'm with us, but I some
Maybe all question we should send like some email, and we clarify all everything, and I think it will be no problem. Okay, Denise?
Okay.
Yes, okay. So thank you again for your detailed presentation and sharing with us your ideas. And the next, our speaker will be Dr. Anastasia Solomenko from the Kurdyumov Institute of Metal Physics of the NAS of Ukraine.
Yes.
Anastasia, you with us, yeah? Okay. So please take the floor.
Thank you. One second, please. Can you see my screen?
Yes, we can see, but not in full mode, just like some, yeah.
F5 and Alt Tab.
Thank you. Thank you. Good afternoon, dear colleagues. My presentation is devoted to the phosphorescence tendency to compress or extend in the direction perpendicular to the stretching or compression.
Sorry. Can you press Alt 5 because we see notation.
I press. I see presentation on full screen.
So I am alone see notation, yes? Or all see notations? Dear colleagues, do you see notations? Notations, I mean text in the bottom of the slide. You see this text or no? Text. Anybody can answer my question?
Yes, we see.
Yes, you see and I see and all see. So can you please, Anastasia, press Alt 5 or full screen, for example?
Something wrong, maybe. Okay. Okay.
If you can at least use your mouth to move the border between the slide and between the notations. You can move down to hide them.
Okay.
No, down. I mean horizontal line. No. Yes. At least in this. Okay.
Taras, thank you very much for your help to
I am
Anastasia.
a co-author, so I have to do it.
Yes, we very appreciate your helpful support.
Там треба було запустити показ слайдів через F5, а потім альтапом перейти.
Okay.
Well, okay.
And in English because it's very important because some people seeing us also who need translate in this.
Okay. So,
please take the phone.
good afternoon, dear colleagues. My presentation is devoted to the phosphorescence tendency to compress or expand in a direction perpendicular to the stretching or compression, known in the literature as the Poisson effect. Science Poisson's relations relates to elastic moduli, bulk modulus, and shear modulus. Our study concerns to the correlation of these mechanical characteristics with electronic structure, namely the band gap of phosphorine. The object of our study is a single-layer black phosphorine, which has been exfoliated from the bulk phosphorus in 2014. This slide reminds the perspective, top, and side views of phosphorine crystal structure. The structure is pocket and so possesses the strongly anisotropy. The lattice is characterized by two main directions, zigzag and armchair. The unit cell and Hopin parameters for the first 5 nearest neighbors are denoted. Table in the slide collects some data from several works where authors report on the calculated Poisson's ratios. In contrast to graphene, for which the Poisson's ratio nu is isotropic, in case of phosphorine, nu is different for two in layer stretching direction, along zigzag and armchair. Moreover, the out-of-layer Poisson's ratio appears and depends on the in-layer uniaxial tensile direction as well. All values in the table indicate an anisotropy in mechanical response of phosphorine. However, they are significantly discrepant and inconsistent. In addition, a negative Poisson's ratio in the out-of-plane Z direction under the uniaxial stretching along zigzag X direction is revealed in some works, at least in the narrow strange range from 5% of compression to 5% of stretching. Such a discrepancy in the Poisson's values, adapted from the literature, contributed to our motivation in the study of the bond lengths, bond angles, and their response on the applied strain. Another motivation deals with the significant literature discrepancy in the band gap values of phosphorine from 0.76 up to 2.1 electron volts, obtained within the framework of different approaches: standard generalized gradient approximation, GGA, or so-called GW approximation, and using different various pseudopotentials, Perdue-Borger-Erzenhof PB or Hertz-Koseria-Erzenhof HC. Motivated by the literature discrepancies in the structural and mechanical characteristics of phosphorine, we study how these characteristics correlates with its electronic structure, or more precisely with the band gap as a function of applied strain. We consider two types of the strains, uniaxial tensile and the shear deformation. Both types can be directed along armchair and zigzag direction. Independently on the strain type, the deformation induced and change of the bond length, and thus the changes the Hopin parameters between different atoms. Due to the extraordinary mechanical flexibility, phosphorine can sustain the elastic deformation up to its failure limits, about 27–13% at uniaxial strain, depending on the stretching direction, and up to 10–13% at shear strains. Interestingly, that in the literature, some authors claim even about higher non-destructive limits, about 48% of deformation along armchair direction and about 11% along zigzag one, and up to 35% of shear strains. To study the structural as well as electronic properties of phosphorine, we use the first principles calculations by the quantum espresso electronic structure simulation package, which includes the DFT. Both figures in the slide show monolayer phosphorine with applied strain along the zigzag direction is more stable than that with applied strain along the armchair direction. In other words, the phosphorine is more easy deformable along the zigzag x direction as compared to the armchair one. It seems understandable if we look at the structure, since there are much more non-zero bond length projections on armchair y direction as compared with those on zigzag x direction. Also, it correlates with available in the literature in plane Poisson's ratios, which are several times higher for zigzag strains in comparison with armchair ones. This slide demonstrates the intraplanar and interplanar bond lengths as a function of the uniaxial tensile strain along zigzag and armchair direction. All dependencies exhibit approximately more or less linear behavior. It's quite understandable that with all different directions of strain, the intraplanar bond length L1 increases with increasing deformation, slightly at zigzag strain and strongly at armchair 1. In contrast to L1, the interplanar bond length L2 increases with applied strain along zigzag x direction. However, decreases with increasing strain along armchair y direction. A similar situation is for shear strain. Firstly, all dependencies of the bond lengths L1, L2 manifest approximately linear dependencies. Secondly, the interplanar bond length L1 increases with increasing deformation along both directions, slightly for armchair shear and little bit stronger for zigzag 1. However, the interplanar bond length L2 remains practically unchangeable with applied strain along both directions. Here we see the intra and interplanar bond angles dependent on the uniaxial tensile strain along zigzag and armchair directions. Interestingly, that the bond angles show an opposite tendency under different direction of applied strain. With increasing the strain along zigzag direction, the interplanar bond angle θ1 weakly decreases, whereas the interplanar bond angle θ2 increases. However, with increasing the strain along the armchair direction in intraplanar bond angle θ1 significantly increases, while the interplanar bond angle θ2 weakly decreases. Another situation occurs for shear deformation. While the interplanar bond angle θ1 greatly decreases for both directions, the interplanar bond angle θ2 remains practically unchangeable as it's for the interplanar bond length L2. Calculated bond lengths and angles allows to calculate the Poisson's ratios and compare them with those available in the literature. These ratios act as input parameters in the time-binding model used to calculate the density of states and therewith extract the band gap value in the phosphorine electronic structure. We describe this model in our recent papers and present on the previous NANO-2023 conference, therefore we do not present in this report. As known, Poisson's ratios relate with elastic moduli and depend on the direction of strain. that is characterize the structural and mechanical anisotropy of phosphorine. Therefore, to examine the correlation between the mechanical and electronic properties of phosphorine, we calculate how the band gap varies depending with strain for different Poisson's ratios. Performing such a procedure, we introduced parameter beta, which describes how the band gap changed with a change in strain. Actually, beta acts an analog of the thermal expansion coefficient or compressibility coefficient. As estimation of the diagram shows, if the strain increases by 1%, the band gap varies by 0.1 electron volts for high ration in the in-plane Poisson's ratios along two directions, and 2 times less, 0.05 for lower ration. Thus, the stronger anisotropy makes it possible to manipulate and control the band gap in more wider range. So we came to the following conclusions. High structural anisotropy of monolayer phosphorine manifests in its mechanical properties, practically in its response to the applied uniaxial tensile and shear strains. Phosphorine is more stable, being strained along the zigzag direction as compared with the armchair direction for both deformation types, tensile and shear. All calculated structural parameters, the intra and interplanar bond lengths, angles, manifests approximately linear behavior under the tensile and the shear strains along both considered directions. The interplanar bond lengths behave similarly with all types and direction of deformation, increase slightly or strongly. However, the interplanar bond lengths can increase, decrease, or remain practically unchangeable depending on the strain type and direction. In contrast to the bond lengths, the bond angles shows an opposite tendency under different direction and tensile strain. However, behave similarly for shear strain. The stronger structural and mechanical anisotropy makes it possible to manipulate and control the electronic band gap of phosphorine in a wider range, which can be used to design its potential application in electronics and straightronics. Thank you for your attention.
Thank you very much, Anastasia, for the time accuracy and also for sharing with us your insights and conclusions. So now we have a short time for QR session. If we have question, please.
Hello, thank you for the presentation. And my question is that in the beginning of the presentation, you showed a table with different literature data, including the data on the band gap value, both in experiments and in different DFT approaches. So, and as you said, this was supposedly one of the motivations of your study. So the question is how your data on the band gap in particular compared to those? And I know that while using PBE, the band gap will be underestimated. Of course, that's a known fact. But the thing is that if you plan on comparing with the experiment in the future, yeah, the question is about this. Are there any experiments that relate the band gap to the stress that exist in the literature? Did you compare your data to them? And another question is, if
maybe better question for question.
Well, yeah, that will be the single question. Did you compare this result specifically with the dependency of the band gap on the strain and stress to some experimental data, if it exists?
Okay, thank you for your question. Now, one second. Okay. I want to show slide. Okay. The question was about this slide. Yes, about band gap. If you can see,
Excuse me, can I join and quickly answer? So you can see from this table that a very wide range of these calculations and experiment. Please pay attention that experiments show 1.5 electron volts. This experiment value strongly coincide with our results that we have published in several two papers, including one paper in the Nature publisher. But of course, we made complex investigations. We made calculation not only within the DFT, where we really use PBE, which, as you said, underestimate. But we used a Binding model with, and this Binding model give results that strongly coincide with experimental one. I can repeat that experimental one result for the band gap of phosphorine is 1.5. And regarding the comparison with the experimental values during the loading, during the applied stress strain, you see currently there are no one experimental results on the band gap of phosphorine being unstrained and much more being sheared. There are some papers about this material which can be uniaxially tensiled along two directions, or maybe isotropically, but there are no one result from experiment about shear stress, about shear restrained this material. Thank you.
Thank you for reply and very perfect teamwork. Maybe we have no time for next question, and it will be possible to do by chatting or sent by mail. Thank you again for the presentation. And I would like to invite the next our speaker, PhD student Andrei Sabchuk from the Taras Shevchenko National University of Kyiv. Andrei?
Yes, I'm here. Good morning. 1 second.
Perfect.
I cannot share now.
Do you need? Okay.
Oh, yes, now I can share. Good morning. The theme of my report is influence of the scale effect on the relaxation process in polyethylene glycol 400. The main attention of researchers is forced on the study of fast transcription of this inclusion in the process of different size and the influence of the chemical composition of the surface on this fast transcription. Much less research is done on the relaxation process that occur in inclusions. The purpose of our works was to investigate the effect of pore size on dielectric relaxation. the presence of terminal OH group with a non-zero dipole moment in the PEC 400 molecule allow us to use the temperature dependence of the real and imaginary component of the complex dielectric permittivity to obtain an idea of molecular thermal mobility. We use the polyethylene glycol for 100. That means that molecular weight of these molecules was near 400. And we use for a sample of pore with back for that this pore was different y by 1 in the size. The diameter of pore we can see on the table on right, and the top question, the top picture is some scan of this pore. The complex dielectric constant was measured in the temperature range from minus 150 degree by centigrade to 50 minus 180 to 55 degree by centigrade. At frequencies 5, 10, 20, and 50 kilohertz. The dielectric properties were studied on an aftermarket installation based on the P583 alternating current bridge and core electrode thermostatic cell with the ability to control the thinness of the samples. The samples were placed in closed polyethylene capsule with which allowed for measurement in the temperature range that includes the region of phase transition. On the graph of the real part of the complex permittivity for polyethylene glycol 400, the picture left. In the temperature range of about minus 30 degrees by centigrade, we see a band. I show it with laser. This inflection shift to the region of higher temperature with increases frequency. On the graphic of the imaginary part of the complex dielectric permittivity for PEC 400 sample in the temperature region of minus 38 degree by centigrade at a frequency of 5 kilogears. A peak is obsessed. The position of these peaks shift to the region of higher temperature with increase in frequency. On the graph of the real part of the complex permittivity for sample with pores, a similar band is observed in the temperature range minus 10 degree by centigrade. As frequency increased, their position also shift to the region of higher temperature. For the sample with with smaller pore, this shift is bigger than for samples with bigger pore. I will see it later. The peaking region minus 32 degree by centigrade is similar for the sample without pores. I show all our measurement for all silica gas, but will not start on it details. On this figure, we can see that the inflection of the graph shift to the region of a higher temperature if the samples is placed in a pore structure. This displacement is larger for small pore. This property of PEC 400 nanocrystal is due to the fact that they are surrounded by a porous matrix. The low temperature peak on the graphic of imaginary part of dielectric permittivity shift to the region of higher temperature too if the sample is placed in a porous system. The smaller pore, the shift is bigger. Let's plot the depends of the temperature of the maximum peak on the inverse radius of pore. We can see that it's this depends is linear. We will analyze the influence of the pore size on the energy parameters of the electric realization in polyethylene glycol 400. After construction, the logarithm f of frequencies from 1 divided on temperature of realization depends, taking into account the experimental data and approximating them with the Arrhenius equation. We obtain the value of the activation energy for the study samples, which are presented in a table right. We can see that there are trend on decreases of energy of activation with decreases of size of pore. So we can say next conclusion. The paper investigated the effect of pore size on the dielectric properties of PEC 400. It was found that when the pores are reduced, the region of dielectric relaxation shift to higher temperatures. It shows that there is a trend toward decreases in the activation energy with decreases for size of pore. The thermal mobility of molecules will be observed as a higher temperature with decreases in the pore size. This makes it possible to adjust the temperature of the biological activity. Thank you for your attention. That's all.
Also for time accuracy and also for sharing with us your data, your results. And now we have a short time for question. If somebody has question, maybe everything is clear. Thank you again for your contribution. And now we will invite our next next speaker. It will be moment. It will be a student Anastasia Davidyuk from the Taras Shevchenko National University of Kyiv. Anastasia, are you with us?
Yes, hello.
Hello, so please take your floor.
Can you see my screen? Yep.
Can see.
Okay, so hello everyone, my name is Anastasia Davidyuk, and today I would like to share with you our research with name Transport of Supramolecular Complexes in Combined Hydrogels based on agar, practice of using a modified photoacoustic method with polymer response enchasement. And first of all, I would like to talk about relevance and purpose of this research. The study of mass transfer process, in particular diffusion and absorption in a dispersed system, is important for understanding a wide class of phenomena in natural media. And the possibility of controlling diffusion process is relevant in such areas as target drug delivery, tissues engineering, and industrial wastewater treatment, and etc. Convenient model objects for experimental studies in this direction are gel-based composites, in particular combined gels based on agar in our experiments. And the aim of the study is to investigate the diffusion of biological molecules in gels and media with sorption using a modified photoacoustic method. And to achieve this goal, we set ourselves the following task. First of all, we wanted to demonstrate the efficiency of the modified photoacoustic method developed by us. Also, investigate the kinetic of photoacoustic response in gels with sorption properties and determine the time dependence of diffusion. And last but also not least, to study the possibility to control mass transfer process in agar-based combined gels. Let's talk about the method of experiments. In general, photoacoustic methods are based on the properties of temperature waves and are highly sensitive to small concentration of the substance absorbing optical radiation. With appropriate geometry of the experiment, it is possible to specially localize within the thermal diffusion length, of course, the gel region from which information of on the concentration of target substance is obtained. Modification of the methods consisting in the use of a polypropylene film as a working body allow to increase the amplitude of the photoacoustic response and its sensitivity by an order of magnitude compared to classical variants. In addition, the measurement procedure was considerably simplified. And to estimate the diffusion coefficients of dyes in a hydrogel, we used a well-known equation, which we can see on the slide is equation number 1. The process of formation and destruction of supramolecular complexes were used to control diffusion. Polymers with chains woven into a gel network, for example, amylose, and molecules with the ability to diffuse into the gel were used as receptors, for example, proteins. The agars from hydrogels that are transparent in the optical range and have properties convenient for use in laboratory practice. At an agar concentration of 1.5 to 2.5%, this gel can be used to make plates. They are easy to cut and transfer and connect with thickness of 200 to 1500 micron thicknesses. almost the entire volume of the gel is occupied by water. The agarose mesh and the agarose mesh size and structure are much larger than the size of dye molecules and most drug molecules. The values of the diffusion coefficient of such substances in gels are not much lower than in water, for example, and monotonically decrease with the increases in the size of their molecules. And the situation is different for macromolecules, with an increase in the hydrodynamic radius to several tens of nanometers. There is a drastic decreases in the diffusion coefficient relative to their corresponding values in water. So, there is a prospect of controlling the diffusion process of target substances by combining them into supramolecular complexes, in particular with macromolecules because of their size. And now we can see the setup scheme, and let's take a closer look at the cell and the physics of this process. The cell we can see here. And yeah, in the modified geometry used in this work, the sample is a two-layer gel, the first layer and the second, plate with a variable dye concentration along the thickness. The sample is separated from the internal volume with air of the cell by a transparent plate of low-pressure polyethylene here. And the polyethylene is in this geometry is working body, as was mentioned, and the photoacoustic signal is generated by bending thermoelastic deformations of the polyethylene layer. And polyethylene is periodically heated by heat transfer from a heat source located in the gel. And these heat sources are formed by the absorption of radiation by the dye, which enters the gel after passing through the photoacoustic cell. So it means that through both its transparent walls, so glass and polyethylene, and also through the air layer between them. So let's talk about results of experiment as well as their analysis. Now we can see that this slide shows the amylose molecule and the supramolecular complex of iodine with amylose, which is the main component of the starch that was used to make the gel for this experiment. So as you can see in the second picture here, we see ring molecule, and this is amylose. And inside of this ring molecule, we can see purple molecules, and there are iodine. So these complexes are basically supramolecular complexes. And first, the graph of diffusion versus time for the complex of iodine with amylose is presented here. And this experiment was carried out as follows. The substrate was an agar-based gel with added amylose, and an agar-based gel which had been impregnated with iodine beforehand was placed on top of previous gel. And the most interesting thing on this graph is that as concentration of starch in the gel increases, we observe a delay in diffusion. We can see it here, for example, for 1 to 1, 1 to 2, and 1 to 3 here. We explain this by the fact that a steep spatial diffusion front is formed. Also to validate the experiment, the diffusion of iodine in a pure agar-based gel was investigated. Here, orange circles, and the calculated diffusion coefficient is quite close to the real values, which indicates good performance of the modified photoacoustic methods. Theoretical is here, black line, and with coefficient of diffusion 750 plus minus 100 micrometers square per second. So next one experiment was diffruxamine with iron chloride. In this case, we investigated the so-called like counter diffusion. So it means that the substrate was an agar-based gel impregnated with one substance, and the second gel was impregnated with another substance and placed on top on previous gel. And here we also can see that by changing the concentrations, here of the both substances, we observe different results. And, oh, sorry, a moment. Yeah. So, where I stopped, yes. This gave us in the future the ability to control diffusion by changing concentration, or also, if we can see here, we also see that diffusion depended by interposition of this gels. So which gel where will be on top or bottom. Also, for comparison of the result, experiments with already formed complexes of diffruxamine with iron chloride were carried out. That is, in this case, diffusion from the gel with complexes into a pure agar-based gel was observed. So we can see orange circle is just iron chloride, and the blue one is for complexes. Also, here it can be clearly seen that the diffusion of the complexes differs significantly from the diffusion of iron chloride alone. And also, we can see here the black and red line. It's theoretical measurement, and it's clearly like close to real measurements. So next, let us consider the diffusion of the complexes of near-top with iron chloride. And it is worth to specify that near-top is a drug, and the active substance of which is ethyl-methyl hydroxyl pyridine succinate. And here we can see that differences are observed not only when changing the concentration, but also from the interposition of the gels. And it's just like for diffruxamine with iron chloride. And also were calculated theoretical diffusion coefficients of iron chloride. And in the end, I would like to talk more about protein diffusion, which I think is the most fascinating. And after all, this is already similar to the practical application of this work, and also coincides with the original goals and relevance, that is the introduction of this development in immunodiffusion and, of course, drug delivery, which was our goals. Basically. And the diffusion of albumin complex with bilirubin was investigated, and it is important to clarify that albumin is a protein, specifically immunoglobulin, which means that it is macromolecules, and its diffusion extremely slow. That's why we can see only this like dot. And the experiments were carried out in two ways. So firstly, the diffusion of the complex into a clear agar-based gel, and the results are shown by the orange dots. And second diffusion of the albumin with bilirubin complex into a gel with also albumin, and the results are shown by blue dots. So The conclusions from this work are now presented on the slide. And as a result of this research, all the objectives was achieved in the particular high efficiency and simplicity of the modified photoacoustic methods in the study of mass transfer process in soft materials are shown. And for most of the studied substances and complexes, the characteristic times of concentration equilibrium establishment were of the order of tens of minutes, which allowed us to study a considerable number of samples. A decrease of diffusion coefficients was found in cases when mobile complexes were formed. This also allowed us to estimate the effective values of diffusion coefficients of target substances both in the free state and in complex. In cases where the complex were associated with the jealous networks and were less mobile, a special behavior in the time dependence of the photoacoustic signal's amplitude was observed, and this particularly cannot be described within the framework of classical theory and is explained by the delay of the diffusion front in a medium with sorption properties. In conclusion, I would like to say that the initially set tasks were achieved and also interesting and useful results were obtained, which encourage further research. Thank you all for your attention. I will be glad to answer your question, and also you always can chat with me by my email, which shown here.
Thank you very much also for your input, Anastasia. It's very appreciated. Now I would like to invite any question.
Sorry, thanks for your presentation. Can you please switch to the slide with Nairotop diffusion experiment?
With Nairotop, yep.
What source is these drastic changes between dark green graph to where ferrum is 5% and light green where ferrum chloride is 2%? What
Okay, so actually this is really interesting question because in real, this dark green and light green are the same, but it doesn't really, we can't really see here. But if we see in here, so in the start of the experiment, so they're really close, and we can see this like peak of light green, which we also can see actually by diffroxamine. And answer would be this peak is a large concentration of diffusing diffundant, yes, so diffusion sample. So its concentration on the surface at the film is just huge. And after this, we have diffusion from bottom gel to upper. Yes, after which the complexes tend to the equilibrium state, and hence the decline of these peaks that will increases.
Okay, thank you very much.
Thank you again, Anastasia. That not more question for you. So have a good luck in your scientific career.
Thank you.
Yeah. So the next our speaker will be student Artur Medved from the Institute of Telecommunication, Radio Electronics and Electronic Engineering, Ukraine. Artur?
Yeah. Greetings, colleagues. Give me some moment to set it up. Okay. So, do you see it clearly?
Yes.
Yes. Okay. Thank you for coming today. I'm Medved Arthur, and I'm looking forward to present to you investigation of magnetoresistance of silicon wires doped by boron and nickel under strain influence. So, as you may know, research in the field of magnetoelectronics has been developing intensively in recent years due to the unique potential of devices developed in this direction. While many studies in magnetoelectronics have been made on metals, semiconductor-based spintronics are still under development. Significant theoretical and experimental studies have been conducted to learn more about spin relaxation in semiconductors. Various compounds of types A3B5 and A2B6 have been studied. However, the connection between the magnetic properties, deformation, and resulting change in magnetic resistance in such structures studied insufficiently, which is important in development of magnetic field sensors, spin valves, or other related devices. So the aim of our experiment was to establish the regularities of changes in characteristic of microcrystals by studying the magnetoresistance at direct and alternating currents in a wide temperature range to assess the parameters of low temperature flow of charge carriers and its application in device of micro and nanotechnology. So first of all, it's necessary to discuss the importance of choosing a filamentary crystal. The most important property of such crystals in general is their unique high strength, which is in several times higher than the strength of massive or mono and polycrystals. As we can see on the table 1, silicon is not inferior to other materials in terms of its parameters. The high strength of these wires is explained by the perfection of their structure and to a greater extent than in massive crystals, the number of volume and surface defects, which plays an important role for the concept of spintronics and in the study of the magnetic properties of such structures. So in our experiment, filamentary crystals of silicon were grown by a chemical transport reaction in a closed pyramid system. The starting material, which is silicon grown initiator, doping impurity, and transporting agent, were loaded into the quartz tube. The temperature of the evaporation zone and the crystallization zone was 1000 and from 70 to 800 degrees Celsius, respectively. As shown on table 2, for research, filamentary crystals were selected in a way that the concentration of the acceptor impurity, which was boron, corresponded to both the dielectric and metal sides of the metal dielectric transition, given that for boron-doped silicon, the critical concentration of the metal dielectric transition is 5 times to the 18th power centimeters in minus cube. Since the charge carriers responsible for conductivity are concentrated in the near surface region of the naturally formed heterostructure of the crystal, they exhibit specific effects such as giant magnetoresistance and hysteresis. To validate this observation, previously we conducted a series of experiments. A crucial step in this research is creating conditions that allow for the control of the magnetic moment with the crystal structure. This makes evaluation of the nickel impurity distribution profile essential, as it directly influences the technological parameters of crystal structure formation, as shown in the image on the right. A more detailed study of the magnetoresistance jump in turn showed that in filamentous crystals, hysteresis of the same magnetoresistance is observed. Such changes may indicate that influence of the magnetic field on the state of bound electrons in the core shell nanostructure. To verify these features and the dominant contribution of the magnetic impurity to the magnetoresistance of the crystals, a transition metal impurity was introduced into the near surface region, as was shown earlier. In this case, the transfer of charge carriers at low temperature will be associated with polarization processes, as evidenced by the magnetization of the crystal on the next slide. As shown on the figure, in fields up to 6 Tesla, there is a jump-like change in the longitudinal, yeah, probably, magnetic moment, and in fields to 0.5 Tesla, there is magnetization hysteresis. This is obviously due to the reorientation of the charge carriers spins along the field when its sign changes, which leads to an inconsistency between the forward and reverse branches of the magnetization. Building on this understanding, the role of deformation becomes critical. By precisely controlling deformation, we can further manipulate the magnetoresistance and magnetic properties of the crystal. This brings us to the next slide, focusing on how deformation impacts these properties. So as the experiment shows, during the tensile of the sample, the surface of the microcrystal tensile is radially compressed, which causes a redistribution of the Thom states, so known Thom states. This leads to an increase in the energy of the trapped levels, which in turn causes an increase in the overall inductance of the sample. Compression, on the contrary, leads to radial expansion, reducing the surface compression at the trap level energy, which reduces the inductance. In addition, it is worth noting the opposite effect on the capacitance of the microcrystal. An axial compression leads to an increase in the radial dimension of the sample, which increases its capacitance. Yes. But under tension, the capacity decreases due to the decrease in the surface area of the sample. Based on the studied deformation effects, the study of magnetoresistance is a logical extension, since changes in the internal structure and surface states of microcrystal directly affects their behavior in magnetic fields. Our studies show that deformation of the crystal leads to a decrease in the value of the negative magnetoresistance. In addition, we observed an expansion of the range of negative magnetoresistance towards higher magnetic fields, especially at the temperature above 70 Kelvin, as shown on the figure on the left. And for comparison, the figure on the right shows the characteristic without any deformation applied, without any strain influence. The observed effect can be caused by the influence of the surface on the electrical conductance of the crystal, due to the existence of magnetic formations in the near surface region, which, after being subjected to deformation, have a greater impact on the transport of carrier in the crystal. Based on the results of the research, it is possible to suggest the use of silicon microcrystals to create high-precision sensitive elements of microelectronics, microelectronic sensor, capable of operating at the low temperature and under strong magnetic fields, with the possibility of integrating sensitive elements with information processing circuits and low cost. Table 3 shows some initial characteristics of such sensors. Thus, the low temperature research leads to several key insights and practical recommendations. First, deformation-induced changes in magnetoresistance are achievable through the redistribution of energy in Thom states. Thus, deformation serves as a powerful tool for controlling the magnetotransfer properties of the crystal, with potential applications in sensors where magnetoresistance can be like negative magnetoresistance can be approximated to zero. And the result of the low temperatures studies, properties of the study material can form the basis of the development of ultra-sensitive magnetic field sensor with the magnetoresistive principle of action. Thank you for your attention.
Thank you very much, Artur, for well-prepared and well-presented your results and sharing with us. And now we have a short time for question.
Yeah.
Maybe yes, we have question, please.
Thank you very much for this nice presentation. Honestly, I'm not the expert in this magnetoresistance area, but the question is, what is the time scale of responsiveness of such sensors if they are built based on these wires? I mean, like, are they responsible to fast change in magnetic fields, or how slow, how fast they are?
Yeah, I can tell that they are pretty fast, but I think we are talking about nanoseconds. I'm also not sure because I was assisting. I was not really participating in the the actual experiment because it was conducted in the Poland. But yeah, they are quite responsive. But actually, can you repeat this question for me again? Because I'm not sure that I got it.
You said something about nanoseconds. If it is like the data you have, it's okay. Okay, for me,
Mm-hmm. Okay, thank you.
familiar with this field very much. Just curious.
Mm-hmm.
Okay, maybe it's possible continue by email and chatting.
Yeah, sure. Yes.
Thank you again for your input and contribution. So we kindly invite the next house.
Thank you.
It's a PhD student Mikhailo Mikityuk from the Lviv Polytechnic National University. Mikhailo, are you with us? Can you hear me? Maybe he has some technical problem. Okay, the next speaker will be student Alexey Nedorozhny from the Igor Sikorsky Kyiv Polytechnic Institute. Alexey, are you with us? Yeah, super. Okay, so please take your floor.
Yeah, can you hear me? Okay, good. I'm glad to present our work simulation of the deformation and breakage of a polyene carbon chain. There is many work dedicated to investigation of the atomic and electronic structure of polyene. However, currently there is not complete understanding how its breakage occurs. So this work dedicated to the modeling of polyene strain properties, and there is a clear interest in investigation polyene deformation as well. Polyene tension diagrams were calculated using the WASP framework that implement safety potential. And instead of the total energies, their bond energies are used. However, we will be call them total energies in this report. The slides show the unit cell which are used in our calculation. In such a cell, interaction between chains was considered practically non-existent, and distance between chains was 15 angstrom. The chain was deformed by x-axis. The calculation was performed taking into account geometric optimization, and the convergence for energy was 0.1 milli-electron volt. The equilibrium interatomic forces were calculated identically to this paper that you can see in the end of slide. The next slide shows the electronic structure of polyene in the ground state. The top figures show the 2s and 2p densities of electron states. The effect of sp hybridization shown as well, and in the lower figures you can see the spatial distribution of electron density in both 2s zones. It follows from these pictures that the hybridization of S and P states is higher in the top 2s sigma zone. The one-dimensional plots of the S and P electron density show this more accurate. And here distribution by Z. The modeling of chain deformation and breakage was performed by changing the cell parameter Z, and the following slide shows the result of such calculation. On the left figure, the dependency of the total energy and interatomic equilibrium forces are shown. And it's shown independence of parameter Z. Calculation have shown that the strain of polyene is determined by the maximum force value. You can see this FC point on the top left graph. And its value 11.5 nanonewtons. It follows from the figure that polyene breaks down into individual C2 molecules. As could be expected, the breakage occurs as a result of a disruption of the long bond, which we will call the contact bond R. The result of the calculation of energy and forces characteristic will be plotted as function of this value R, and you can see this on the right plot. And when we replotted this, this allows us to compare the deformation process of cumulen and polyene. And the result of such a comparison are shown on the right figure. The cumulen strain, 16.5 nanonewtons, is significantly larger than the polyene strain, 11.5 nanonewtons. Unlike polyene, cumulen breaks down into individual atoms. And the polyene deformation process appears to be much more complex than the cumulen one, and it contains several stages. And these stages we will discuss in more detail on the next slide. Calculation have shown that polyene deformation leads to a short bond length as a complicated function of the contact bond. It first increases to a maximum value A and then start to decrease. This stage is described by significant changes in the electronic structure of the polyene. The direct gap in the chain increases from 0.32 at ground state to 2.8 electron volt at point B. Point B is the point of maximum force from previous slide. At this point, and after this point B, another structure, another modification of polyene appears. This phase has two properties of typical polyene. First, the existence of energy gap, but now it's indirect one, and value of this gap is decreases to 0 when we tension it. Second, there are two types of interatomic bonds, short one and long, like in typical polyene. And the long bond increase at the short, long bond increase and short bond decreases. At the beginning of the third stage, point C, the short bond length increases and then decreases to become equal to the bond length in molecule C2. And to analyze the deformation and breakage process of polyene, it is necessary to calculate the interatomic interaction within the C2 fragment and the interaction of the fragment among themselves. And the result of such calculation are shown on the next slide. The left figure shows the dependency of energy and interatomic forces between C2 fragment. At all stages of chain deformation, the interaction energy of the fragment continuously decreases. You can see this from left bottom plot. After for an extreme, this interaction is practically a non-existent. The interaction force between the C2 fragments at the first stage increased to 12.5 nanonewtons. And what is interesting and should be noticed that this value is greater than the force from slide number 3, where was the total force. This calculation shows that the reason for this is a particular aspect in the short bond interaction between the carbon atoms in the C2 fragment. And this calculation inside the C2 fragment shown on the right figure. At the third information stage, the interaction between the two carbon atoms in fragment C2 decreases and then begin to increase. The minimum value is at point A. It's the second point after ground state on the right bottom figure. And then it decreases to up to point B at same graph. At the second information stage from the ground state to be different stage, the repulsive forces that are plotted on the right top graph between the two atoms also increases and then decreases to 0 and becomes an attractive forces. And this force is the reason that the equilibrium force in the chain is less the interaction force of the two C2 fragments. At the second information stage from B to C, the modified polyene is stretched. At the same time, the interaction energy of C2 fragments decreases and energy of two atoms within the fragment increases. The force of attraction between the two atoms in the fragment increases and then decreases. I mean this like something like parabola from B to C. At the beginning of the third stage of deformation at point C, jumps in the energy and strain of interaction and strain of interaction between the two atoms in the C2 fragment occur, and as a result, weakly interacting C2 molecules are formed. It's red dashed stage on the plots. And the formation of the molecules is illustrated on the next slides. Here, for comparison with point C, the spatial distribution of electron density at the first two stages are given as well. The spatial distribution of electron density in the 2p zone and the bonding and anti-bonding 2s zones at a different stage of stretching is shown. Here is ground state, the first column, the second point B is a maximum force, and C plane breakage. Like concluding this work, I can say that the process of deformation and breakage of infinite chains of cumulene and polyene have been studied. As a result of polyene breakage, C2 molecules are formed for cumulene individual carbon atoms. The cumulene chain was found to have higher strength 16.5 Newton than the polyene chain 11.5 Newton. The energies and forces of interatomic interaction in the process of polyene chain deformation have been calculated. It is shown that the certain stage of polyene deformation interaction forces arise between the carbon atoms in the C2 fragment that are bounded by a short bond. It is established that this effect leads to the breakage of long bond contact bond between the C2 fragment and the breakdown of polyene into molecules. As well studied was the evolution of the electronic structure of polyene during deformation has been studied. The spatial distribution of electron density at all stages of chain deformation has been investigated. Thank you for your attention.
Thank you very much for your presentation. Your results are greatly appreciated. And now time for question. Is something? Yeah, please.
Thank you very much for this nice report. Just curious, in the beginning, you mentioned that you use method for calculation, which is published elsewhere. But for the non-expert, could you please just say what kind of approach is used for such calculations, just to know?
You mean this first slide? Okay.
Calculating such properties.
I use the implemented in WASP pseudo-potential method.
Okay, thanks.
Something else interesting of our auditorium, right? So thank you again for your input. And now many thanks to all for effective work and contribution in section work. And we have now break for lunch, and we will have next section. We will have next session which is dedicated to nanochemistry and biotechnology at 2:15 p.m. And you all warmly invite to join it. So see you soon.
So, dear colleagues, let's continue our work for today. We will move forward to our next session, Nanochemistry and Biotechnology. The first speaker from this section will be Dr. Roman Nebesny from the Lviv Polytechnic National University, Ukraine. Dr. Roman, can you start?
Hello, dear colleagues. Can I share my presentation?
Of course, please.
Okay. Can you see the slides?
We can see, but not a full screen mode. Please stop sharing the screen and then choose the right windows with full screen mode.
Is it better now?
Yes, it's full screen mode. Please start.
So, first of all, let me introduce myself. My name is Roman Nebesny. I'm from the Department of Technology of Organic Products, Lviv Polytechnic National University. And here is my presentation. At our lab, we work a lot of different catalysts. We develop catalysts in order to accelerate the synthesis of different organic products. And mostly we use the heterogeneous catalysis, I mean solid catalyst. But in recent years, we were inspired by enzyme catalysts. For example, the enzyme catalyst which consists selenium species. And we had an idea to synthesize some kind of synthetic enzyme. So, as you see on the pictures, for example, like glutathione peroxidase, it's an enzyme which contains selenium species, and it has quite high catalytic activity. I mean, extremely high selectivity at mild reaction conditions. And it was the idea to synthesize some kind of synthetic catalyst. And in case when the catalyst is synthetic, it is possible to extend the range of reaction conditions. First of all, temperature, the ability to use different solvents, organic solvents, or different pH of reaction. So we decided to synthesize some kind of microgel. Microgel is a smart material which can change its physical and chemical properties under some external things, for example, temperature or pH, so we can control the swelling degree or like this, and it helps us to separate the catalyst after the reaction. And as you see here, we synthesize the base of our catalyst, microgel catalyst, was polyvinyl caprolactane, and here we used some kind of crosslinkers. We had two kind of crosslinkers, one permanent crosslinker and one selenium-containing crosslinker, which is catalytically active. We prove via different technique, for example, Raman and NMR spectra, that we really synthesize the proper catalyst, which contains selenium species. And it was at the next stage, it was very important to choose the test reaction, and we decided to choose the reaction of acrylic acid synthesis or mass acrylic acid synthesis, because We have a lot of different catalysts from industrial processes, the catalyst for oxidation of propylene, or the catalyst for aldol condensation of formaldehyde with acetic acid to obtain acrylic acid. And it was very interesting to compare the general solid catalyst, which also has some industrial implementation, with the new one kind of catalyst, microgel catalyst, and to compare the catalytic activity and also the energy consumption, because in most cases solid catalysts can be used at really high temperatures, I mean 300 degrees or higher, or 400 degrees. And here you can see some fast testing. We test our catalyst in different solvents, for example, in dioxane or methanol. And here you can see the graph when we use the dioxane solvent and the catalytic activity of different microgel-containing catalysts. And here you can see the concentration of the selenium-containing selenium species in catalyst. And in the case of dioxane medium, the only target product, desirable product, is acrylic acid with quite high yield, in some cases more than 90%. And this graph shows that when we use the methanol as a solvent of our reaction system, we can obtain at the same time two target products. So this is methyl acrylate and also some small amount of acrylic acid. And the total yield is also higher than 900%, which proves our idea that this kind of enzyme mimicking catalyst can be really highly selective. And as you see here, the reaction was carried out at 50 degrees, so it's quite mild reaction conditions. It was really important to show that we can reuse our catalyst. And on this graph, you can see then after 3 catalytic cycles, the yield of acrylic acid of our target product remains at quite high. As the problem is some difficulties in catalyst separation, because we used some kind of filters and some catalyst was lost at this stage. But of course, we can improve the technique of catalyst separation and reuse. And also it was interesting to show some technological things. We start from the study of effect of selenium containing species, for example, 2 mol% to 5 mol%, and also to study the effect of our permanent cross-linker. And we found that the optimum concentration of selenium containing species is near 2%. So there are no reason to increase this concentration. And also we studied the concentration of our catalyst, of our microgen catalyst in reaction mixture, the effect of temperature and the reaction time. As you see, it's quite general dependence. The temperature higher, the yield is higher. It's always, all of these things are quite general. And this graph demonstrates that besides the acrylic acid or methyl acrylate, we can change the solvents to ethanol or butanol. And in this case, we can obtain acrylic acid and acyl acrylate, or also we can acrylic acid and butyl acrylate. So our system is suitable for synthesis different kind of unsaturated acids and also the esters. And here we try this system also to synthesize crotonic acid, mesacrylic acid, and ethyl acrylic acid. And in all cases, we have quite good results. As you see, the yield of ethyl acrylic acid or mesacrylic acid are lower compared to acrylic acid, but the same situation is can appear when we compare with industrial catalysts, including solid catalysts. At the next stage of our study, it was very interesting to test our catalyst in interfacial reactions. In this case, we used, for example, toluene as a solvent. And in this case, as you see, we have two phases, oil phase or toluene phase and water phase. This kind of processes quite often are useful because in case of two phases, in some cases, it is easier to separate the reaction products because we can just can work with water and oil phases separately. And as you can see here, using our catalytic systems, nano-containing system, microjoules, we obtain quite good results. And at the temperature of 90 degrees, we obtain the yield of benzoic acid over 90%. This graph shows also that when we compare some small molecular containing systems here, for example, and here, in case of microjoule catalysts, the yield is higher. And the other important thing is when we carry out the reaction at 90 degrees, we have quite high yield, and this proves that our synthetic microjoule catalysts are catalytically active at higher temperatures. And for example, the selenium-containing enzymes are not active at these temperatures, and they can be used only up to 40 degrees or even less. Here also some comparison and some demonstration of our catalytic system, for example, with different concentration of or ratio of water and oil phases. And also we, in recent months, we switched to some other kind of microjoule catalyst. We play with some size of molecules which contain selenium species, and they are connected to the microjoules. As I mentioned, it was PVCl or polyvinyl caprolactam based microjoules. And so we improved the selectivity up to 98% in case of benzaldehyde oxidation to benzoic acid. And the same at the same time, it also can use different solvents. For example, when we use octanol instead of toluene, we can also obtain two target products, I mean benzoic acid and octyl benzoate. And also this new kind of catalyst, as you see from the previous graph, has higher conversion, higher selectivity, and of course the higher yield. So our ideas was quite successful. And in this case, like a conclusion, we can say that selenium-containing microjoules proved to be highly effective catalyst for oxidation of unsaturated aldehydes, and we can obtain very high one-pass yield of our target products, and at the same time the selectivity of target products are higher than 98%, and only water we detected as a byproduct. And also our systems have high catalytic activity on the interface of oil and water phases systems, and this help us to think about different new reactions, especially in biotechnology or medicine, which I believe will be the main fields of application of this microjoule containing catalysts. At this time, it's all. So if you have some questions, you can ask me. I will try to answer.
Please, do we have any question?
In any case, it is better.
Mail. So once again, thank you very much, Dr. Roman Nebesny. And we will move forward. According to our program, it should be Professor Helena Pruntsova. Professor Helena, can you hear us? Are you here? I can see Professor Helena. I know that she has some problem with electricity probably now. So we will move directly to the next speaker, PhD student Darina Mruga from the Institute of Molecular Biology and Genetics of the NAS of Ukraine. Darina, can you start?
Yeah, hello, just give me a moment, please.
Yeah. Please take your time.
Maybe it will be better if next reporters start now, because we were going a little bit late earlier than the schedule. That is why I need 5 minutes or something like this.
Okay, then I ask Oksana Kremeny, are you ready? Oksana, can you hear us? Please, dear participants, according to our program, we have some delay, and because of Darina needs some times. If anybody from the next session probably ready to start, please raise your hands, and we will give you a word. Maybe Oleg Dmitriev. As I understand, because of the shift in our program, our participants not ready to start now. Then we will make a 5 minutes short break to contact next speaker. So I announce 5 minutes break. Dear colleagues, we have been contacted by our participant's PhD, Oksana Kremen. She told that she is ready to start her presentation. So be ready to hear the speech from the Oksana Kremen from Chuiko Institute of Surface Chemistry of the NASA of Ukraine. Oksana, please take your floor.
Yes, good day. Can I start to share?
Yeah, you can start, please. Yeah, now it's good on full screen. Please start.
This hexagon-shaped polycyclic aromatic hydrocarbon functionalized by oxygen functional group and single vacancy DFT study. A huge attention is focused on finding ways to reduce the cost of methanol conversion to dimethyl ether or formaldehyde, and the main road to reduce the cost of methanol conversion is the development of carbon catalysts. There are presented experimental work where carbon materials, carbon nanotubes, activated carbon, and graphene materials are used as catalysts. But reaction mechanism of methanol conversion in carbon materials are still under discussed. Graphene is a crystal formed by a two-dimensional system of sp2 carbon atoms, and carbon nanocluster was obtained by cutting up graphene sheets from 6 sides. And polycyclic aromatic hydrocarbons was formed by saturating the CNC edges by hydrogen atom. As a model of graphene-like materials, we use such as polycyclic aromatic hydrocarbons and its derivatives. The active reaction center of graphene-like materials in the case of surface of crystalline solids are defects in the crystal structure. 2 cases of methanol interaction were considered with foreign defect of polycyclic aromatic hydrocarbons, single vacancy I, with structure functionalized by oxygen group like carboxyl group and hydroxyl group. The structure optimization of derivatives was tested with different multiplicity, and the ground electronic state was found. The ground electronic state of cluster with single vacancy is triplet. The spin density is localized on carbon atom number 1, and this atom is an active site for methanol interaction. The first step of interaction is the dissociative absorption of methanol by breaking of OH bonds in methanol molecule and bond carbon 5 carbon 6 in 5-membered ring of the cluster. The angio effect of corresponding reaction is exothermic. The next stage of interaction is breaking the CH bond of methyl group and leads to simultaneous formation structure is a bridge. The energy effect of corresponding reaction is exothermic. 2. The next step is breaking two bond carbon 6 oxygen and carbon 1 carbon with formation of molecular of formaldehyde. The energy effect of this reaction is endothermic. The slide presented the stages of the interaction of polycyclic aromatic hydrocarbons with single effect with methanol molecule. The positive energy near 112 kilojoule mole shows that the reaction is endothermic. Therefore, the reaction proceeds only at elevated temperatures, which is typical for dehydrogenation reaction. The transition stage between C and D stages was found. With dissociative absorption, breaking the charge bond of methyl group, formation the bridge structure, and desorption of formaldehyde molecule with restoring the bond at the carbon 5 carbon 6 in the 5-member ring of molecular of polycyclic aromatic hydrocarbons. And we considered the cases where structure was saturated by oxygen group like carboxyl and hydroxyl. The interaction of two methanol molecules with hydroxyl and carboxyl group shows that on the first stage the physical absorption is occurs. The next we consider different cases of interaction, cases with when the water molecule was present in reaction and when water molecules was removed from the reaction. Energy profile E between methanol molecular and hydroxyl group into account molecular water molecule and energy profile when water molecule was removed. And the slide presents the energy profile with interaction between the methanol molecule and the carboxyl group. Pictures are when the water molecule was present, and picture B when the water molecule was removed. The reaction is exothermic, and the presence of the water molecule provides a lower binding energy for the second methanol molecule. And conclusion, vacancies in polycyclic aromatic hydrocarbons in active sites in the dehydrogenation reaction of methanol molecule. The presence of the dangling bonds of the carbon atom lead to the formation of a bridge structure and the formation of formaldehyde and hydrogen molecules. Oxygen functional groups like hydroxyl and carboxyl are activated sited in a dehydration reaction, and the presence of the water molecule provides a higher binding energy for the second methanol molecule in the reaction of methanol dehydration to dimethyl ether. And thank you for attention. Can you hear me?
Yes, yes, we can. Thank you very much for the good and interesting report. Do we have any question? Okay, I can see questions. So thank you very much once again. And we will return to our previous speaker, Darina Mruga. Are you ready now?
Yes, yes, I am.
So please share your screen and start your presentation.
I hope you can see my presentation now.
Not yet. Oh, okay. Now we can see it. Please start.
Okay. Good evening, everybody. My name is Darina, and I'm going to show you my presentation, which is named Creation and Characterization of Magnetic Polymer Microbeads. It was made in the Helmholtz-Zentrum Dresden-Ressendorf. So, what was the idea of my work? It's not. Why is it? Okay. So the whole idea of this work was to create new small micro engines that could move under the gradient of magnetic field. And the novelty in this work is to put the small nano or microparticles that has these magnetic abilities inside the bigger shell. That is why when we need to remove this part from everywhere, or for example, environmental environment or from the body, we can make it in one piece. So there is no need to worry about some missed magnetic nanoparticles inside the body or environment. To create this, we took the commercial magnetic microparticles that were made from the iron oxide and from polystyrene. And to enshell them, we decided to use polyethylene glycol diacrylate polymer that is polymerizing under the ultraviolet light. So here you see the video that shows the possibility of such movements. The magnet here is not really strong, so it should be very very easy to move them and control their position. So what was used to create them? To create these microparticles were used a microfluidic system that contains the pumps, microfluidics, syringes, tubes, and etc. The internal diameter of the tube was 500 microns, so it's quite big. And the forming of the particles was made by mixing two unmixing phases. It's a water phase with the polymer and magnetic particles, and the oil phase just to separate just to create this little droplets. So on the right corner, on the right upper corner, you see the video of creation this polymer droplets in the real time. And on the bottom of the slide, there is a video of polymerization, these droplets also in the real time. And then they were collected in the tube to further analysis. Here you see the video how the analysis of their speed was taken. So it was the high-speed camera. We switch on the magnet, and then we calculate the speed for each microsphere, each bit that you see here. So we started with the analysis of the polymerization time on the formation of the microbead. And we found that on high concentration of microparticles, it's 2%, we need quite long time of polymerization of minimum 1.22 seconds. At the same time, when we use a lower concentration of the microparticles, we can make polymerization quicker, but it also leads to the softer form, so they are not so so hard in feeling and touching. That is why we decided that we will use 2.24 seconds as an optimal, but it depends of your purposes. So if you want soft bits, you may use lower time. And such dependency of the concentration we explained by the light absorption by the microparticles. So as you see, there is a table which compares the light absorption of the different components of the polymer mixture. And as you see, the microparticles absorb quite a lot. It's about 2 units, and other are smaller. Also, we checked the dependency of the speed of the particles from the time of polymerization, and we didn't find any dependencies, so it doesn't change anything. Also, we create, just to try, we create microbits with bigger particles inside them, but they sediment really quick. That is why the homogeneity of these bits is really low, and it's not really useful. Also, we try to create Janus form of these bits, so they are not homogenic but polar. It was made by adding extra magnet during the producing and polymerization of these particles. And you may see a really interesting form, interesting order of these microparticles that is follow the magnetic lines during the polymerization. So the conclusion on influence of UV polymerization is that a higher concentration of microparticles require longer UV exposure. Long polymerization time leads to the segmentation of the microparticles and poor homogeneity. And also polymerization time doesn't influence the speed of the microbits. So also we test the influence of concentration of these microparticles on the microbit characteristic. And we found that maximum possible concentration inside the bit is 2%. When it's higher, they are not polymerizing due to high absorption of the light. The lower concentration as you wish, but you need at least 0.05% to move these particles under magnetic field that we tested. And we tested magnetic fields from 40 millitesla to 240 millitesla. And we found that the dependency of the speed is quite linear to the concentration of the particles. The speed of the particles is also quite linear to the intensity of the magnetic field, so it's logically. The same was made for the Janus microbits, but the dependency of the speed here was not the same, and it could be explained by the process of the polymerization. So you put the extra magnet and you have local increase in the concentration of microbits where they start to absorb light a lot. That is why the polymerization here is not made. So we have not really sphere microbit, but it's a little bit cutted in the part where the microparticle concentration is really high. So here you can see that when the concentration of the microparticles was 1%, the polymerization was made quite good. But when the concentration was higher, it was not made properly. So the amount of these microparticles inside one bit is lower than it should be. We also measured the average weight of microspheres, and it was interesting that we found the dependency of the time polymerization on the weight of the bit. We explained it by the swelling of the bit. So when the bit is not polymerized for a long time, it have the ability for swelling. So it takes water and becomes more more weight. Obviously, homogeneous microbeads have higher weight than Janus microbeads, and we are not sure about the influence of the particle concentration on the weight of the bead. Oh, I have misprinting. Here should be temperature. So we also tested the stability of the microbeads under different temperatures. It's important in case if these particles would be used in the high temperature environment, for example, body, or I don't know, hot lakes. And we found that during 7 hours of observation, there is no changes in the microbead structure, maybe a little bit slight color, but it's not about the polymer destruction. It's more about the destruction of the ink that was put inside these particles, just to visualize them during the producing process. And at the end of the work, we tested the hysteresis of these microbeads to ensure that they are not magnetized under the gradient of magnetic field. And in case if we shift the direction of this magnetic field quickly, our parts will also respond to this magnetic field. And as you see, the hysteresis line are almost the same in the both directions, from minus to plus and from plus to minus. That is why we showed that these particles should react really quickly. So thank you for attention. Here is on the slide my conclusions, that we produce our microbeads, that we tested them. We showed the possibility, their stability, and we assure that they have high potential in for using in different spheres. For example, for further encapsulation in larger spheres, for using them as a micromotor, and then releasing this micromotor from the environment. Also, it could be the surface could be functionalized for the drug delivery applications, and it also could be used as a small micro manipulator to move something inside the water phases. Thank you for attention.
Thank you very much for your presentation. Do you have any question? Okay, I can see questions, so thanks once again. And I invite the next speaker, Dr. Oleg Dmitriev from Lashkaryov Institute of Semiconductor Physics of NASA of Ukraine. Dr. Oleg, can you hear us?
Yes, I hear. Let me start with my... can you see my screen?
You now share the screen with Zoom. You should share the window with presentation.
Okay, let's start.
Okay, now we can see your presentation in full screen mode. Please start your talk.
Okay, thank you for invitation to this conference, and good afternoon to everybody. So my talk is devoted to studies of application of ethyl cellulose matrix to thermally activated delayed fluorescence emitters. This work was was done in due to the three different research institutes. The materials were synthesized in Kaunas University of Technology, and research work were performed in Linköping University and Institute of Semiconductor Physics. So first of all, I would like to introduce what does thermally activated delayed fluorescence emitters mean. So these materials become interesting from not about 10-15 years ago, when a group of Japanese researchers showed that TADF molecules can produce a very nice photoluminescence, and not only photoluminescence, but also electroluminescence. And these materials were used in production of organic light emitting diodes with relatively high external quantum efficiency. The mechanism of operation of these materials is shown here on this energy scheme. The specific of these molecules is that they have triplet energy levels very close to the first excited singlet energy level. The energy gap between these energy levels is of the order of 0.1 electron volt or less, and therefore that means that electrons which populate the triplet energy levels can be excited by thermal energy, for example, at room temperature, and populate the first singlet energy level from which the molecule can emit light. Why this process has advantages? Because triplet photoluminescence or phosphorescence usually requires low temperatures, and it is vulnerable to oxygen. It can be quenched by usual atmospheric gases. Therefore, a singlet photoluminescence is more preferable. Therefore, when we have injection of electrons to the triplet energy level in electroluminescence devices, we have a population of triplet energy levels with due to the electron spin statistics, the most of electrons populate triplet energy level. About 75% of electrons go to triplet energy level, and only 25% of electrons go to a singlet energy level. Therefore, dependent on the gap between singlet and triplet energy levels, we can see if phosphorescence, if this gap is relatively large, or we can produce a reverse intersystem crossing, and the electron can come from triplet to singlet energy level, from which we can produce singlet thermally activated delayed fluorescence. If we look at the common structure of TADF emitters, they usually consist of donor and acceptor moieties linked with the flexible linker, which allows rotation of donor groups in respect to acceptor by a specific dihedral formation of specific dihedral angle. And also, this structure allows a charge transfer excitation. That means when we excite this molecule with light, the donor groups provide electron, which goes to acceptor. And in this way, we have the change in the conjugation length of the molecule, which shown here as an example. You can see that after the excitation, we have extended conjugation length of the molecule, which means that this molecule produce emission with a longer wavelength. And this emission, which is due to the charge transfer, the Jablonski energy scheme is shown here of these processes when we excite electron to the singlet energy level, then this electron can go to charge transfer energy level and emit light from this energy level to the ground state. A specific feature, specific property of these emitters is also the twisting, a conformational change due to the rotation of donor groups in respect to the acceptor group. And this twisting produces different dihedral angle between donor and acceptor groups, which assist in charge transfer state formation. Also, it assists in the intersystem crossing between triplet and singlet energy levels. This illustrates here by this aromatic molecule, which change the conformation from the flat to the distorted one, and dependent on the level of distortion, this molecule produces a different triplet quantum yield. The higher the twisting, the larger the triplet quantum yield of this molecule. That means that the twisting conformation assists in intersystem crossing and photoluminescence of these molecules. And also the change in dihedral angle can control the energy gap between singlet and triplet energy levels. And in principle, we need the smaller energy band gap in order to better populate the singlet energy levels from the triplet one. In this work, we used 4 different TADF emitters, which are shown here. Specifically, the upper 2 molecules have the same donor groups, but these donor groups are different from the different ends of the molecule. You can see that construction of these donor groups have different chemical structure. And also these molecules are different by the acceptor group in the central part of the molecule. And the second part of the TADF emitters consists of the same donor groups, but different acceptor groups. So we took these 4 molecules and compared their photophysical behavior. Here you can see the comparison of the absorption and emission spectra of these molecules, and from where we can see the relatively large Stokes shift of the photoluminescence in respect to the photoexcitation patterns, which varies depending on the structure of the molecule. But our purpose was to use a specific matrix to deposit these emitters, because usually for production of organic light emitter diodes, TADF emitters are deposited in some matrix. As a matrix, researchers usually use small molecules which are whole or electron transporting materials. And specific of application of small molecules is that for production of these structures, we need thermal vacuum deposition, which is rather expensive technology. Instead, in this work, we selected the polymer, ethyl cellulose polymer, which has advantages because it helps us to produce samples with a cheap spin coating technique. And second, This material, ethyl cellulose, is environmentally friendly material, and therefore it has specific advantages for the preparation of photoluminescent structures. Here you can see the fluorescence microscopy images of the samples deposited in the matrix and deposited without matrix. On the right side, you can see the images deposited in the matrix, and on the left side, you can see dye molecules spin-coated without matrix on the substrate. And you can see a large difference in homogeneity, because in the polymer matrix the sample is much more homogeneous. And the second specific is that photoluminescence of the samples prepared in the polymer matrix is much brighter compared to the samples prepared without matrix. And quantitatively, you can see the difference in relative quantum yield of the photoluminescence in the matrix shown by red curves, and dye film prepared without matrix by black curves. The difference is more than 1 order of magnitude for this sample, for example, which is a very huge difference. And also what we can see from this data is the different position of the photoluminescence spectra, which give us the different color of the photoluminescence. And normally the photoluminescence of these molecules in the polymer matrix give us the blue shift in respect to the photoluminescence of the neat dye films. Similar results can be seen for the other pair of dyes. Again, we can see the more homogeneous distribution of dye in the polymer matrix. And also we can see the huge enhancement of photoluminescence of the dye in the polymer matrix. And also we can see the different color of the emission. In order to clarify the mechanism of photoluminescence enhancement in the polymer matrix, we studied the dyes in the different solvents in order to compare how the solvent polarity and viscosity influences the photoluminescence spectra. So here we selected tetrahydrofuran, chloroform, and acetone with which have different polarity and viscosity, and we concluded from this data that usually solvent with lower polarity and high viscosity produce more brighter emission of photoluminescence. Also, you can see the difference in the spectral position, which give us the different color of photoluminescence. And for example, acetone solution give us the red shift of the emission, which agrees well with the charge transfer character of the photoluminescence of these specific dyes. So then the next step I want to show is the comparison of solution film and dye photoluminescence in the polymer matrix. And here we can see we do not see the systematic change of the spectra in the polymer matrix compared with the solution spectra, for example. In some cases, we see the redshift of the photoluminescence maximum in the polymer matrix compared to the solution. In some cases, we see the blue shift of photoluminescence. So we cannot conclude that polarity of the polymer matrix influences the emission intensity. In addition, we also I should note that matrix, ethyl cellulose matrix itself produces a weak photoluminescence in the blue region near 400 nanometers, which is responsible for the emission of the dye in the polymer matrix for this components of the in the blue region, which contributes to the general emission of dye in the polymer matrix. So we can conclude that polymer matrix assists has some synergetic effect in improvement of emission of TADF emitters in the polymer matrix. But of course, this effect should not be high because the quantum yield of photoluminescence of the ethyl cellulose matrix is very low, is about 1% or less. Therefore, we cannot rely on this effect, and most probably the matrix improves, the polymer matrix prevents the rotational motion of the molecules, which assist in enhancement of the quantum yield of photoluminescence. So I would like to make conclusions of this work. First, I showed that ethyl cellulose matrix can be used as a successful matrix for application of for preparation of TADF emitters, and it results in very cheap technology and relatively good, smooth morphology of the samples. Second, I showed you that the application of this matrix results in a huge enhancement of the photoluminescence by about 1 order of magnitude. And third, the mechanism of this huge photoluminescence enhancement most probably is related to synergetic effect of emission of both TADF and the matrix, or probably energy transfer from the matrix to the dye molecules, together with freezing of rotational motion of the emitters. But of course, we need further studies in order to clarify this mechanism in more detail. I would like to acknowledge people who helped with studies of these materials and our financial bodies. And I would like to thank you for your attention.
Thank you for your presentation. Any question? I don't see any question. Thank you for your presentation again. Go on to the next speaker, Dr. Anton Ovcharenko from Karazin Kharkiv National University, Ukraine.
Here, our results. My name is Anton Ovcharenko. I work at Kharkiv National Karazin University. While my Presentation is loading.
Just a moment. Oh, you can
Excellent.
start.
Thank you.
Sorry for technical
thank you.
problem.
Today I'm going to present you some results on our numerical simulation of anti-reflection coating for solar cells, potential solar cells applications based on silicon on insulator gratings. Already introduced myself. I'm a specialist in optics and photonics, but my talk touches the solar cell area, so I will briefly glance through it. The semiconductor photonics is based on using high optical refractive index semiconductors, first and foremost silicon, which absorb light and generate the current based on active carriers. How exactly it works is beyond the scope of this work. Important for us is that the modern system can harvest around 20 to 25% of the incoming radiation, which can be considered high or low depending on which angle you look at it from. If we look at how the modern commercial solar cells looks like, it consists of a few layers. In the middle, we have our semiconductor solar cell layer. Then we have some structural element, encapsulation, glass coating, etc., etc. One of the major factors that lower the efficiency of the solar cell is, unsurprisingly, the reflections that are introduced. First and foremost, we have the reflection on the air and glass interface. There are of about 4%, which can be calculated using Fresnel equations quite straightforwardly. Then we have bigger reflections on the glass or encapsulation, depending on which material it is exactly, and the solar cell, the high refractive index material of about 30%. So together, these reflections are about equal if we used the air silicon interface directly. They sum up to about 30–40%, depending on exact materials and on the wavelengths of interest. So it's obviously a huge amount of energy that we would like to take back. So obviously, people have been looking at this problem using various methods. Our weapon of choice, so to speak, today would be periodic arrays of such nanoscatterers or nanostructures. These arrays might be known to you as metasurfaces because of emerging properties due to the periodic or sometimes aperiodic alignment of the structural elements. The applications for these devices include polarization control, directional propagation, some selectivity, enhanced absorption, localization, surface effects, etc., etc. The application range is vast. Here, we're going to use them to reduce the reflections from the surface. So if we look at our simplified problem, as we do in, for example, a university course, we start from the interface of the two materials, silicon, which is optically thick, stands for the solar cell itself, and air for the surrounding medium. This can also be glass or some other encapsulant, but the qualitative picture stays the same. We can always add a single layer of some homogeneous material, sometimes referred to as single layer anti-reflection coating. Its thickness defines its resonance wavelengths where the reflection can be perfectly cancelled. However, when we deviate from these resonant wavelengths, the reflection rapidly rises. Similarly, if we simply add two of such resonators, we will have two resonance frequencies. And by making the structure more and more complicated, in theory, we can further dampen the reflection. Indeed, this is one of the most popular using this thin film stack, so-called. It is one of the most popular ways of reducing reflection. But the fabrication can be challenging because it's effectively a sandwich of very thin layers of different materials. What we want to do, so yeah, what we want to do is to have some metasurface on the interface, which will be crucially single layer, still optically thin, but a single layer, and that it will have a better performance everywhere, maybe except for the resonance area, where really this thin film shine, yeah, around the resonance, but everywhere else, our structure, we hope, will perform better. And here for comparison, yeah, we'll have a typical reflection of an uncoated substrate. You can see everywhere above 30, maybe even 35. So our structure of choice for this work was this funny looking hybrid geometry, which consists of a combination. It can be considered a superposition of a cross geometry and a circle, both very well known in the nanophotonics community. The design process here simply consists of trying out different combinations of these geometric parameters, just simulating the reflection values in this our charging wavelengths range of interest, which covers the whole visible and some infrared spectrum, and choosing the best combination, which we'll think of as the optimal design. This approach is nowadays, it's often termed to as forward design approach. Before it was the design approach, now it's forward design approach. Why? Because many people consider also the inverse design approach. Inverse design approach means we start from an objective, which in our case is the minimal reflection, and we change the refractive index in the cross-section of our unit cell so that it becomes something which is as close to our objective as possible. So we start from a random distribution of our material, which is obviously, it's like a gas of silicon, which is fiction. Yeah, and we iteratively, step by step, converge to some finite size, smooth looking structure, which can be fabricated. For this, the algorithm that we use is called GLONET. It was first introduced around 2019 by the group of Professor Jonathan Fan in Stanford. Very simply, it's just a loop which is executed automatically on a computer, which iteratively updates this picture closer to something like this picture. This happens to be our final design, where it step by step improves our objective metrics. And crucially, during this optimization, our structure is not represented by a simple image as here, which is intuitive and straightforward for a human, but rather it uses some high-level abstract representation using a generative adversarial network, deep neural net, which we can consider right now just an implementation detail. All right. So this is the slides of our results, similar to the slide you've seen before. We have this is just the reflection of bare silicon. We have this, which is a single layer. In this case, I took the dispersion of silicon nitride, which has the intermediate refractive index, which is the closest to our ideal case. And the two devices, forward and inverse design one, have their reflections over here. You can see we still have some areas where they reach 0.1, so 10%, which can be quite high. But overall, we have we're much improved compared to single layer thin film stack, even up to 3 thin films. It outperforms them, as shown in more details in our paper. The average reflection is 2.35 and 2.33 for the invert design one. So from this, we can draw two quite interesting, somewhat opposite conclusions. First of all, the invert design does work a bit better. This is one conclusion. The second one, better, but not by much, which is interesting by itself. It means that for this quite constrained but an important problem, even such a relatively simpler, well-known tool as a forward design can be enough for the majority of cases, and like using something new, modern, and more complicated is not always necessary. But at the same time, if you're very sensitive to obtain the very, very best, then maybe it's worth the try. Yeah, the similarity between two can be used visibly. They are visibly similar, even though they were obtained completely independently. So yeah, this might not necessarily have been a cross, but it happened to be a cross like something that we use here. And you also see that the resonance patterns are similar. Indeed, the field profile at one chosen wavelength confirm that the mode that's excited, that is responsible for the anti-reflection properties, is the same mode. Lastly, if we're gonna use it for the solar cell design, obviously the light doesn't come only straight from the normal angle. It also comes at an oblique angle. So we simulated our designs as a function of the incidence angle to obtain the final figures averaged over the incident wavelengths and angle. They are obviously higher because for a larger angle, we have this high reflection area that's related to the emergence of the first diffraction order in the reflection, which we unfortunately cannot do anything about. But yeah, we can at least minimize these absolute values. So finally, a comment on the future steps we would like to take. It's obviously to take into account during the optimization the incidence angle. At the moment, it's quite hard to do because the number of simulations rise dramatically. There has to be developed some smart approach how to do it. Then we would like to experiment with a multi-layer optimization. Sure, it will complicate our setup somewhat, but we hope to reach even better and better figures. Also, it's interesting to incorporate another objective to have a multifunctional design at the end. And with this, I conclude, and I thank you for your attention.
Thank you for your presentation. Any questions, please?
Would you please tell us what are the sizes, projected sizes of your, I don't know, pattern?
Yes, thank you. It's an important question. I didn't want to complicate it with some figures, but yeah. So we consider the period is an important metric. To obtain the best performance, it has to be smaller than the smallest wavelengths we have, because otherwise we would have diffraction, which increases the reflection. So we experimented with values from 300 to 400, and we stopped at the value of 380. So this allows us some wiggle room with. So this the smaller the value you have for your period, the farther back you have this stop. So the smallest it is, this area decreases, it becomes here, but the overall reflections here gets higher, and so your average is also higher. Yeah.
So you said only about the period, and what about the height of this and the size of each element?
Yeah, the height is also an important metric. It's 150 nanometers, both forward. So for both this design and this design, they're both 380 here and 150 in size. And the inner element, where they're here to scale. So I don't remember exactly, but you get the idea.
Okay, about 100. Yeah. Thank you.
Sure.
Thank you. A short question: if your patterned structure absorbs some part of energy?
Yes, that's a great question. Here in the simulations, we considered lossless silicon for the main reason being simplicity and again efficiency. Because in reality, we want to, for practical applications, we want to maximize transmission, right? It's not about reflection, it's about transmission. But if we do not have absorption, we can really look into reflection, and it's just numerically much more efficient. So we can because in transmission we have orders, and in reflection we do not. It's much more computationally efficient to look at reflection. So that's the main reason. So considering real and absorption of silicon, really it's quite low, above maybe 500, 550. So around 400, 450. Yeah, it's absorptive, maybe with the imaginary part being up to 10% of the real part. But other than that, it's quite low absorptive. So oftentimes, I guess the majority of works just neglect the absorption part.
Thank you for the question and again for your presentation. We go to the next speaker. The next speaker should be PhD student Kahina Amari from Mohammed El Bachir El Ibrahim University, Algeria.
Good afternoon. Good afternoon, everyone. Please, could you see the share screen?
Yes, it's okay. You can start your presentation.
Good afternoon, everyone. My name is Kahina Amari, and I am pleased to present my research on the semi-empirical calculation of K-beta-1 X-ray fluorescence cross-section for lanthanides, specifically elements with atomic numbers between 58 and 71 at an energy of 123.6 keV. I will break down my presentation to several key points, starting by an introduction. Then I will moving along the method used to calculate the semi-empirical computation. After that, I will explore the results and discussion, and finally a conclusion. Let's start with a brief introduction. X-ray fluorescence is a powerful analytical technique widely used for element analysis across various fields, from material science to environmental studies. Among the different X-ray lines, the K-beta-1 lines are particularly significant for analyzing the elements. Accurate determination of K-beta-1 X-ray fluorescence cross-section is crucial for enhancing the reliability of quantitative analysis in different applications, such as atomic and molecular research, radiation physics and dosimetry, medical research, and etc. In this study, we focus on the semi-empirical determination of K-beta-1 X-ray fluorescence cross-section using an analytical fitting function to model the experimental data. This approach not only addresses the inherent challenges in X-ray fluorescence cross-section measurement, but also aims to provide a more accurate and generalizable understanding of the underlying physical process. This study is very important because understanding the K-beta-1 fluorescence cross-section for lanthanides is essential for various applications, including material science, nuclear physics, and environmental studies. Lanthanides have complex electronic structures, which makes theoretical calculation challenging. By incorporating experimental data into our semi-empirical approach, we can refine theoretical prediction and achieve more accurate cross-section. Throughout this presentation, I will discuss the methodology employed for the semi-empirical measurement and the analytical function used for the fitting and the results obtained. Before proceeding further, let's first define what we mean about X-ray fluorescence cross-section. X-ray fluorescence cross-section typically refers to the probability of a particle X-ray transition within an atom. When an atom is exposed to incident X-ray radiation, there is a likelihood that an inner shell electron will be ejected, and an electron from a higher energy level will transition to fill the vacancy, emitting characteristics X-rays. For the K-shell, the X-ray fluorescence cross-section is related by a simple relationship involving the fluorescence cells and the X-ray emission rates for various transitions to the K-shell. So the theoretical K X-ray fluorescence cross-section is calculated from the following expression. However, in our study, we slowly focused on the transition K beta 1, which is the transition from K shell to M3 subshell, that is expressed by the formula below. Now I will outline the methodology we used. Our methodology involves several case steps. First, we collected experimental data on K beta 1 fluorescence cross-section for lanthanides with atomic numbers ranging from 58 to 71 at 123.6 K. We then calculated the weighted average values using the following expression from the experimental data as well as the ratios R using the given expression. And we present these results in the following table, which is a summary of the experimental sigma K beta 1 for element from Z equal to 58 to Z equal to 71, include also the excitation energies, the references from where the data are obtained, and the weighted average values and the ratios. Noting that these results have been recently published by our groups, Amari et al. In the second step, to establish a reliable semi-empirical K beta 1 X-ray fluorescence cross-section, the ideal technique is to fit the experimental data for all elements at an energy of 123.6 K. Once we have obtained the weighted average values, we plotted the quantity sigma K beta 1 weighted as a function of Z and then fitted them using an analytical function as shown in figure 1, which presents the distribution of the weighted average values as a function of atomic number Z, and the fits are represented by a fall line. The function used for the fit is an exponential function given by the given expression, where the A, B, C are the fitted coefficient given in the table 2 with its errors. After obtaining the fitted weighted average values, we proceed to plot the ratios R as a function of the atomic number Z and fitted the data using a second-order polynomial of the given form, where Figure 2 is the distribution of the ratios as a function of atomic number Z, and the fits are also represented by a fall line, and the fitting parameters are given in the table 3. Noting that to obtain the semi-empirical cross-section, we used the expression below, which is the product of the function fz and gz. Moving on the results, the semi-empirical results are summarized in table 4. This table shows the K beta 1 fluorescence cross-section for lanthanides calculated using our fitting method. These values provide a more accurate representation of the cross-section at a given energy. Then empirical methods. The data reveals consistent trends across the lanthanides series, demonstrating the effectiveness of our semi-empirical approach. To validate our results, we compared the calculated K beta 1 cross-section with the original experimental data as shown in figure 3. Figure 3 that shows that there is a strong agreement between our semi-empirical values and the experimental values of Ertugrul and Apaydin and Terashoglu. This consistency highlights the reliability of our fitting method and confirms that the semi-empirical approach effectively enhances the accuracy of the calculated cross-section. To quantify the accuracy of our approach, we calculated the root mean squares deviation between the semi-empirical values and the experimental values using the given equation. And it is worth noting that our results agree quite well with orthogonal experimental values within the error range of 4.83% to 16.01% for all the whole of elements. Besides, our findings are in excellent agreement with the experimental values of Abidin and Terashoglu, with deviation varies from 0.13% to 6.99% for all the elements. The low root mean squares values indicate that our method accurately models the experimental data, validating the effectiveness of the analytical function used in the fitting process. The strong agreement between our results and the experimental values suggests that our semi-empirical approach is both reliable and can potentially be extended to other X-ray lines and elements, making it a valuable tool for X-ray fluorescence analysis in various scientific and industrial applications. In conclusion, we can say that our study successfully determined semi-empirical K-beta-1 fluorescence cross-section for lanthanides using a fitting method. The strong agreement with experimental data confirms the accuracy and reliability of our approach. This research contributes valuable data for the scientific community and lays the groundwork for further studies in this area. Thank you for your attention.
Thank you for your presentation. Any question? We have no questions. Thank you for your presentation again, and we go to the next speaker. The next speaker should be PhD student Amina Zidi from Mohammed El Bachir El Ibrahim University, Algeria.
Could you tell me, please, if you can see my presentation?
Yes, it's okay. You can start your presentation.
Good afternoon, everyone. My name is Amina Zidi, and I am a PhD student at University of Mohammed El Bachir Ibrahimi, Algeria. I would like to start by thanking the conference organizers for the opportunity to present my work today. Today, I want to talk about L-gamma to L-beta X-ray intensity ratios, a semi-empirical study of lanthanide series elements. In this presentation, we will explore our research in 5 distinct parts. Firstly, we will begin with the introduction, where we will outline the context and objectives of this study. Secondly, we will analyze the distribution of the experimental L-gamma to L-beta values across different atomic numbers. Moving on the third part, we will examine the semi-empirical values of L-gamma to L-beta intensity ratios. In the fourth part, we will compare our values with other studies. Lastly, we conclude our presentation by a conclusion. Let's start with the introduction. Intensity ratios play a significant role in nuclear spectroscopy and atomic physics. Extensive research across different disciplines has been dedicated to these quantities, resulting in their summarization in several comprehensive review articles. Investigating these parameters for elements on the periodic table has been a primary focus of various experiments, along with growing theoretical interest in recent years. In this study, we calculated new semi-empirical L-gamma to L-beta intensity ratios. Then the obtained values have been compared with published experimental values. Definition. The intensity ratio is an atomic parameter representing the ratio between two transition lines. Theoretical intensity ratios of X-ray lines Le to L alpha from the L shell have been determined using the following equation, containing costerochronic transition probability, the X-ray emission rate, the fluorescence yields of the Le subshell, and the ionization cross-section. This figure shows a diagram of the main radiative transition according to the Sierban, UPAC, and electronic configuration notation for the L subshell. For example, if the electron comes from M5 level to L1 level, we denote it as L alpha 1 line. All electronic transition must respect the following rules. Let's now turn our attention to the second part. This figure shows a distribution of the experimental L gamma to L beta values according to the atomic number Z. The examination of this figure indicates that elements with Z equal ranging from 57 to 71, known as the lanthanides, are included in our coverage. Dysprosium, holmonium, and terbium have the highest number of the experimental data points. Moving along to the third part. Table 1 summarizes the experimental intensity ratios and their uncertainties for elements with atomic numbers ranging from 57 to 71, including weighted average values, and along with the corresponding references. This data is sourced from our paper by ZD et al. 2024. The weighted average value is calculated using the following formula, and the internal standard deviation is determined by this formula, where n is the number of experimental data points, and this is an nth experimental intensity ratios, and this is the uncertainty associated with the nth experimental value. With the intention of calculating semi-empirical L gamma to L beta X-ray intensity ratios for elements ranging from 57 to 71, the method used the well-known formula. Following that, we plot this quantity according to the number, according to the atomic number Z, as shown in this figure, where L gamma to L beta W is the weighted average value. Then we have fitted those values by a first order polynomial as follows. Subsequently, we plot the ratio R against the atomic number Z, and then fitted the points by a simple first degree polynomial as seen in this figure. From equation 1 and 2, the semi-empirical intensity ratios can be expressed using the following equation. This one. Let's see now the comparison with other values. To make a better comparison and understand the difference in values more clearly, we calculated the relative error using this formula of RD. This helps us compare our results with those from different references. As we can see in figure 4, our present values are in good agreement with those obtained by orthogonal 1996, where the deviation ranging from 2.13 to 16.22%, except for the Z equal 71 and 72, where the deviation is 25%. Furthermore, There is an excellent agreement between our results and experimental values proposed by Oz et al. 2004 within a range of 1.08 to 6.34%. In general, the comparison between our semi-empirical results and other values reveals a good agreement. In conclusion, in this study, we used a database of L-gamma to L-beta X-ray intensity ratio values. Subsequently, the weighted average value for each element has been calculated. After that, new semi-empirical average L-gamma to L-beta X-ray intensity ratios have been obtained for elements ranging from 57 to 71. A clear correlation was noticed between our values and other studies. And thanks for your attention.
Thank you for your presentation. Any questions? Yes, we have one question.
Thank you for your talk. If I understand correctly, you took a series of experimental results and feed them by some model. And in this case, a reasonable question, if your model can give some prediction or new values or new physics, what you, not just to fit in an existing result, what new results could you produce with your model?
Could you please repeat the question?
Okay. You have fitted a series of experimental results and find some fitted function. Which new results you can obtain from your model? Say extrapolation to another elements which have not been measured or something like this. Okay, then it will be a question for future.
Thank you for your question and thank you for your presentation. And we go into the next speaker. The next speaker, PhD student Oleg Demyanik from Karazin Kharkiv National University, Ukraine. Can you start presentation of Oleg Demyanik?
Hello, everyone. My name is Oleg Demyanik, and the topic of our research is enhanced prism-coupled chiral sensing with plasmonic gratings. Let's start. Okay. Let's start with describing the object of our research. Our task is to develop a method to enhance chiral sensing. Let's start with the concept of chirality. Chirality is the ability of the corresponding object to have the mirror image, which is not identical to the original. And in electrodynamics, if we have a chirality in the medium, then the material equation changes, and we can see that electric and magnetic fields are mixing with each other. And also we know that the chiral molecules have the same chemical and physical properties, but they show significant differences in biological activities. And as example, you can see the molecule of thalidomide. The right enantiomer of thalidomide is sedative, and the left form is very harmful for the human body. That's why it's so important to have a technology that can allow us to separate the chiral molecules. And since the separation of the chiral molecules is a difficult task, so the goal of our research is to develop the method that can allow us in separate very small concentration of the chiral molecules with high accuracy in the real-time regime. And before we move to chiral sensing, a brief explanation what is surface plasmon polariton is and and how plasmonic sensor works. Surface plasmon polariton, it's a kind of electromagnetic waves that propagate propagate along the metal dielectric interface and exponentially decay in the perpendicular direction from the surface. And the main advantages of the surface plasmon is that it's highly localized, very close to the surface. And it should be noted that the surface wave can be excited only by a wave with tempolarization. So we using exciting through prism in Kretschmann configuration to coupling our plasmon. At the boundary of the two media, we have there is a phenomena of total internal reflection. So when we have incident wave, then all the radiation of the incident wave will be totally reflected from the boundary at a certain critical angle. But if we in the reflection coefficient, we can see the drop to zero. Oh, sorry, we don't. In this case, we don't show the drop to zero. But if we add a metal film, then all the energy of the incident wave will be transformed to the energy of the surface wave, and now we can see the drop to zero in the reflection. Now, if we somehow change our substance, then the refractive index changes accordingly, and we can see that the resonance will be shifted to some angle delta theta, and for wavelengths it's works the same, and the ratio between the refraction between the reflection coefficient and angle or wavelengths, it's will be the sensitivity of our sensor. It's called the refractive index sensing. And now, if we add a chiral layer under our metal film, then the small response in the TE polarization appears. And if we look in reflected waves with right and left circular polarization, we can also see that our resonance are shifted by some angle, and the sorry. Oh, okay. And we can see that the delta theta linearly depends on the chirality parameter, and it is this is the sensitivity of our sensor. Now we introduce the differential reflection coefficient through the reflection coefficient in the right and left circular polarized waves, and we can see that where in time polarization we have a drop to zero on this under the 60 angle degrees, and the small response in TE polarization also under the 60 degrees. We see that the in differential reflection coefficient appears maximum. So by this value, we analyzed our sensor. Accordingly, then the bigger our peak value, the better detection of our chirality. And now we need to improve our sensor, and it's necessary to develop such nanostructure that can help us increase this response in TE polarization. That's why the next step we move from the thin metal film to nanogratings, and as a result, we see that we achieve increase our sensitivity of our sensor more than in six times, and the main result of our works is that we found the optimized design of the gold nanograting, and we achieve the improvement of enhanced of differential reflection coefficient by around two times in comparison with the thin metal film. And our figure presents differential reflection coefficient. In the insert, it's for the gold film, and we can see that that we achieve enhanced our differential reflection coefficient almost in 100 times in comparison with the gold film. So by this result, we can say that the simple measure will allow us to define what kind of enantiomers consist our substrate. Thank you for your attention.
Thank you for your presentation. Any questions? Yes, we have a question.
Thanks for your presentation. I have one short question. What form had your gold grating?
We have a period of our grating. It's 260 nanometers.
And it's slit type, yes? Slit form or other?
Yeah.
Thank you.
You have questions?
What is the mechanism behind your enhancement of signal due to grating? How do you think? Actually, it reminds me the same mechanism, like it's named electromagnetic mechanism of enhancement in surface enhanced Raman scattering, surface enhanced infrared absorption, and so on. There is a number of phenomena that have similar mechanisms. Maybe it's also your case. They are also related to plasmon peritons.
No,
Is it? No. At present, you don't know. Huh? Thank you.
The last question, please.
Thank you for your presentation. As I understood, you used one type of your molecule. How do you consider to use other molecules like sensitive layer? Or it's works just with one molecule, or you may use some of the molecules?
We have a medium when we have where we have some chiral molecules, and we don't know it's molecules that's it's something good or something bad. Something maybe it's drug or it's poison. And by this method, when we see in the different differential reflectance by this value delta theta, by this value, okay. By this value, we can identify what the enantiomers we have in our substance. I don't understand, yeah, your question.
You use just one target molecule for a drug. May you use other molecules, or you should manufacture other sensor for other types of chiral molecules?
No, we can use different type of chiral molecules.
Is your sensor universal for different molecules?
Oh yeah.
Thank you.
Thank you for discussion and your report. We go into the next speaker. The next speaker, PhD student Oleg Yermakov from Karazin Kharkiv National University, Ukraine.
Now it's better. Yeah. Okay, my name is Oleg Yermakov. First of all, thank you for the organizers and for this event. What should I do? I love Uzhhorod a lot, and I spent several days with my family. You know, this kid stuff, visiting nice places, having a meeting with colleagues from Uzhhorod National University and Institute of Electron Physics, and of course, training conference reports whenever you find time and place. So, and I would like to congratulate you with National Flag Day, and some of you maybe of this day of Kharkiv City. Okay, now switch to science. Last year, I told about the optical fibers, what they are, different applications. They're used for telecommunications, medicine, sensors, quantum technologies, endoscopy, etc. But there is one problem. we called it in-coupling efficiency. So if we illuminate with plane waves on the interface of the fiber, what is the efficiency of transformation of plane waves into the guided fiber modes that can propagate for kilometers with negligible losses? Under normal incidence, it's pretty ideal, but it rapidly drops with oblique incidence. It drops so quickly that under angles of 15, 20 degrees, it's too low for practical applications. And to resolve this issue, we follow lab-on fiber concept that assumes nanostructure in the fiber and faces. And we propose that axial symmetric dielectric rings made from why dielectric? Because they have negligible absorption losses. Axial symmetry gives us the independence on the direction, so it doesn't matter the signal goes from west, south, or east. Only the angle of incidence matters. And the structure is almost polarization independent. And it acts as the axial symmetric diffraction grating, which first diffraction order coincides with the fiber axis. I skip the details of analytical and numerical models they used to optimize the structure, but then my colleagues from Leibniz Institute of Photonic Technology in Germany fabricated the structures using quite difficult electron beam and ion beam etching procedures. And here you can see the main result. So these are 7 single mode fibers. The central one is unstructured and all other have different number of rings. And this is the measurements results. So we measure this coupling efficiency. Please pay attention, and this is logarithmic scale here. And this gray dashed line corresponds to the bar fiber without nanostructures, and color lines to some nanostructured fibers with different number of rings. And one can easily see the enhancement of in-coupling efficiency by several orders of magnitude at large angles, where this is the main challenge to do. We go further and develop the more advanced technology to produce the nanostructures. It is nanoprinting, or it is well known as direct laser writing, assuming 2-photon polymerization. It allows us to produce the structures during minutes or tens of minutes with good precise, and we can control now the width and height of each ring, the period between any 2 rings, and it opens another degree of freedom. For instance, we can do the structure that consists of 2 types of rings and open second diffraction order. Here, the dashed line corresponds to the simulations, and solid lines to the experimental measurements. And we have 2 local maxima here in angular spectrum. We can do a periodic nanostructure where each nanoring is separately optimized, and we have quasi-flat angular front. That means that we have quite high coupling efficiency at any angle of incidence. And this comparison table shows the range of angles, colored range of angles, where we achieve the necessary coupling efficiency. So for fiber without nanostructure, it's up to 10 degrees. But for the structures with single pitch, it's just the same rings, we have the enhancement at small angles and in the vicinity of the resonance. But for the structure shown here, we cover almost whole angular range. We can do another thing. We can do the nanostructures that consist of several sectors corresponding to different nanostructures. I call this pizza grating, and we use Gaussian beam, focus it on the core region, and we activate, let me say, all or several, in this case 4 types of nanorings that gives us integral good enhancement up to 10%. And maybe the best result today is the using of multi-core fiber. So we use the fiber that has diameter of about 100, 150 microns, and it has 7 cores. And the light propagating inside each core does not interact with other one. So all 7 cores are absolutely independent. And now we put the different nanostructure on different cores aimed to couple the light from different angles. It looks like this. So if we measure the coupling efficiency, we have the maxima at different angles, coupled to different cores with different nanostructures. And this is the integral figure. Lines correspond to the simulation, dots to the measurements. And this gray and black line, this is unstructured fibers. So we can see extremely high enhancement of the coupling efficiency here. And again, if we compare the range of angles, we cover almost whole angular range with even higher coupling efficiency up to 1%, or several percent. And what is also important here is that we developed the algorithm, analytical algorithm, quite simple. Just simple formulas that allow to obtain the initial design of these nanorings for your specific task. So anyone can take this formula, this algorithm, and find some very close to the best designs for some specific tasks. From the other hand, we can use this nanostructured multicore fiber as the angular demultiplexer or collector. So now imagine that I have undefined source that illuminate on the nanostructured fiber, and in 2 meters, I have the output, which I see through infrared camera. And this is the signal from the infrared camera, what I see at the output. Here the angle, the incident angle changes, and different cores are illuminated depending on the angle of incidence. So in other words, depending on the combination of illuminated cores, I can detect from which angle the light comes quite easily. This is real-time measurement. And I can do the inverse task. I can illuminate in several angles by illuminating different cores. Okay, and of course, we can do it with not only single mode, but multi-mode fiber. Here, the analysis is a bit more difficult, but the main principles are the same. And here are the experimental measurements. This graph shows how strong is the enhancement. And beyond the numerical aperture, we have the enhancement. And for the angles larger than 45 degrees, we have the enhancement in several thousand times. Okay, and I think that all these results may be well summarized by this one figure, showing that fiber with proper nanostructure can enhance the light coupling efficiency by several orders of magnitude. In addition to this topic, I would like briefly mention that we drew some other directions, such as surface waves in 2-dimensional materials and structures, spin orbit photonics, and especially the theory of optical beam shifts, optical fibers, we said. Some recent directions, this is manipulation of Brewster angles with 2-dimensional nanostructures. We can engineer the plasmonic resonant nanostructures to obtain the predefined specific properties to control the resonances. We developed the new platform for flat optics to control the polarization of localized waves. And this, you can obtain the details at the poster in the hall, and some other directions that will be discussed a bit later by the next speakers. When I say we, I mean our group that consists of mainly students with average age of 24 years. And the most reports in this section are done by these guys. And of course, in collaboration with very experienced and professional colleagues, researchers. And the last part, I would like to announce that we plan to launch the Ukrainian Optical and Photonic Society to combine the efforts related to the development of optics and photonics in Ukraine with international support. And when I talk about it, many people ask me, what is the statute, what is the constitution? And it a bit triggered me because this is just formal rules, while I think that the most important things that are values which we share. And in principle, we have 7 main values. First, this is honesty, transparency, and reputation. So no plagiarism, no falsification, visible and transparent financial operations. Second, this is competence and qualification. We live in the world of incompetent leaders, and this is inaccessible for us. Our main aim is breakthrough science and high impact research. Yes, we do publications for grant reports, but this is not our main goal. And we know that our main goal, this is really, really breakthrough researches that usually take years to do. We make the stress on the young professional and leaders. Of course, we're glad to collaborate, to receive the consultations and advices from experienced researchers, but still we believe that the main force should be the young guys up to 40 years old, approximately. Fifth principle, this is love for Ukraine has no borders, and we understand 2 concepts here. First, we have clear Ukrainian and anti-Russian position. And second, we believe that any Ukrainians, we neglect the borders, and any Ukrainians outside Ukraine, or even foreigners that share our principles and values, are welcome to be involved and join us. We open to new directions, to new subjects, and we focus on interdisciplinary research. So photonics, optics, and biology, photonics and chemistry, photonics and astronomy, photonics and nuclear physics are very welcome. And we would like to develop these directions. And finally, we aim to constant development and self-improvement. At this, I would like to stop and thank the armed forces of Ukraine. That's unbelievable that we can do science even under these difficult circumstances. Thank you.
Thank you for your presentation. Please, question.
As far as I understand, the refractive index of your material is very important. So I have 2 small questions. One, did you calculate or maybe estimated the influence of the refractive index? And second, what was the refractive index of this grating?
Yeah, thank you. Very good question. Indeed, it's important, and the higher is the refractive index, the better for us. For the very first case that I shown, it was silicon nitride with refractive index about 2 in the near infrared range, almost 2. And this is quite good. For nanoprinting, we are very limited by the materials because it's a polymers, and polymers have quite low refractive index. And in our case, it was something about 1.55. And this is very low, and I was very doubt that it will work because the refractive index of the core is 1.45 or 46. So they are almost the same. But still, as you see, it works. Yeah, and it proved that even polymer works, surprisingly, but good for us.
So there is no possibility to use like slabs of very thin slabs of crystals with high refractive index. There are crystals like potassium tantalate, which has tens of units refractive
To
index.
date, it's too difficult technologically. To date, I hope that in future I will wait when our colleagues, technologists, will be able to produce at least silicon. It will open another opportunities for us. But to date, it's too difficult to have the precise, good, high quality structure. So we work with what we have.
What material are your nanostructures made of? Is that some polymer material?
Exactly. This is some kind of polymer. I don't remember the title exactly, but this is some polymer with refractive index of 1.55 at the telecom wavelengths of 1.55 microns. Easy to remember.
Okay, thank you for presentation. I have two questions, one very short, maybe it answered yet. What is the space between the rings filled with?
It is air.
Okay, thanks. And doesn't this technology of fiber require more frequent restoration of light beam in the fiber?
Sorry, could you repeat?
Doesn't this technology require more frequent light beam restoration in the fiber?
More frequent restoration. I don't understand this term. What do you mean under this term? Do you mean during the fabrication procedure or after the light propagates?
After the light propagates.
No, the properties of propagating light doesn't change at all, because this is just the guided mode, and this is the only solution that can exist inside the fiber.
Okay, thank you.
For one last question.
Yeah, first of all, I'd like to thank you for this amazing presentation. I'm truly impressed. Just one small question about the slide number 10. Yeah, as far as I remember. Just, you told me about that there exists some formula that you can apply and to get the properties required for some tuning of the photonic light propagation. Could you please tell more about where this formula comes from, and is it empirical? Is it first principles?
Very good question that I waited for. So the simple formulas may be so simple like this, and it works. So the circles correspond to the most optimized cases, and the line to the simple formulas. From there, from where they came. So I calculate the overlapping integral between the fields of the guided modes and the field scattered by the nanostructure at the fiber interface. So I calculate the overlapping integral between the tangential fields. Here we have the cylindrical system, so I have some Bessel functions there, but very surprisingly that if you will check the integrals analytically, correctly, the answer is very simple, especially for the cases when the cores are much larger than the wavelength. The wavelength is 1.55, the core diameter sets about 10 microns, so that condition helps us in this case, and the formulas become very simple. But I can give more details, so they will be published soon. And I think in the first paper, in supplementary materials, there is also with some mistakes, but more or less good analytical theory.
Thanks for discussion and for your presentation. The next speaker, student Artem Hrinchenko from Karazin, Kharkiv National University.
Good afternoon, dear colleagues. My name is Artem Grinchenko, and the topic of this work is engineering of plasmonic anisotropic nanopatch-based metasurfaces. And what are metasurfaces? Metasurfaces are two-dimensional periodic surveillance array of elements that is their period is less than the wavelength and their thickness is 10 times less than the wavelength. And we can distinguish two applications of metasurface in far field, that is, they can transform electromagnetic waves falling on them, completely reflect them, absorb them, change the polarization, or focus them. In this case, if you look at dispersion diagram, that is, it depends on frequency on the wave vector, we work in the middle of light cone. And this line corresponds to the wave vector in vacuum. However, for such applications, that require planar technologies such as various on-chip devices and optical circuit optical integrated optical circuits. We need to deal to localized light, and that is the wave vector should be larger than the wave vector in vacuum. That is we should go under the light cone in this zone near field. And we can note the hyperbolic type of metasurfaces. Let's first look at isotropic case. Here, the depends of the surface conductivity of a resonant two-dimensional structure on the wavelengths is shown. And you can see for some wavelengths, for imaginary part is positive and after resonance is negative. The case after resonance corresponds to ordinary metals. And now let's trace these nanoparticles by adding some degree of anisotropy, and this resonance will split into two, and another regime will be formed, namely hyperbolic. And now we can plot the isofrequency contours. That means the dispersion in all directions. For isotropic case, this column, and anisotropic case, right column. And you can see for isotropic case, depending on the wavelengths, contours will be just circles. And for anisotropic case, we see the topological transition. We start from horizontal ellipse. Next, we see two modes. One becomes close to the light circle, and another one becomes a wide hyperbola. And next, we see a flat easy frequency contour that characteristics canalization regime. And the last one, we see the vertical ellipse. And where this hyperbolic regime is used, hyperlensing, for example, laser sensing, for example, sensors, and spontaneous emission enhancement. It's very interesting and very important things, but to design this metasurface, it takes a lot of time. And our goal is to develop practical guidelines for engineering of plasmonic and isotropic metasurfaces with specific predefined properties. And how will we analyze this hyperbolic regime for our metasurfaces? Let's take a metasurfaces with consisting gold nanopatches with rectangular cross-section and square lattice. Then, depending on the direction of electric field along X or Y, we will have the following reflection spectrum here. And we need the framework of effective models. We replace these metasurfaces with a layer with two-dimensional conductivity which obeys the Drude-Lorentz law according to this formula. Solving the Fresnel formula with such a conductivity layer, we have find the reflection coefficient of the total reflection. For the intensity, we'll have the following form. And further, we approximate the values of sigma 0, beta, and gamma by a method of least squares and obtain the corresponding surface conductivity here. And now we can determine the spectral bandwidth of hyperbolic regime is the maximum value of the resonance wavelengths of lambda x minus the maximum values of resonant wavelengths lambda y, which show a vertical dashed lines on figures B2 and C2. And finally, we demonstrate the main results of this work. First of all, we analyze the dependence of resonant wavelengths and delta lambda on geometric parameters and anisotropy factor for metasurface based on gold nanodisk with elliptical cross-section. As you can see, in case when we change the anisotropy factor, our resonant wavelengths are strongly divergent. That means lambda x linearly shifts to the red spectrum and lambda y linearly shifts to the red blue spectrum. And according from figure A, we see the same for delta lambda. Linearly depends when we change the anisotropy factor. And now we derive a universal empirical formula here. And to confirm the correctness of our formula, we introduce the relative error and plot the corresponding color map here for better visualization. And we can see for most cases, the relative error doesn't exceed 10%, which is a good result for our formula. In the same way, we analyze the resonant wavelength, depends of the resonant wavelengths and delta lambda for gold nanopatch based metasurface. We start with a square nanopatch and stretch it to extreme cases, and in other words, to rectangular gratings. We introduce the filling factor along the stretching direction as a fix and determine it as a long side of nanopatch normalized by the period, and plot the corresponding depends on it here. And when we change the site of nanopatch, we can see how one of the resonant valence lambda y begins increase quadratically from the value of fx equal 0.85. At the same time, other resonant valence lambda y continue increase linearly from all range of fx. At the same, we see for delta lambda, it's rather unusual in specific result. And the next slide, we show one of the interesting practical application of plasmonic anisotropic metasurface. And when we transfer signal in a plane, and in a plane in normal regime, we experience a lot of energy loss. And for solution this problem, we need to achieve a canalization regime, which allows the propagation of localized wave in the fractionless and highly directional way in a single direction. And by choosing this stretched nanopatch, we realize this specific regime for our metasurface design. And this canalization regime observed when one of the imaginary components of the surface conductivity is large and another one is near zero. And we can see pronounced peak at 1000 nanometer. But for most effective canalization occurs at the wavelengths slightly offset from the resonance wavelengths. And this is due to high losses near the resonance. And which is characterized by a large real part of surface conductivity red line. And in the conclusion, results of my report were published in these articles, and one of them was even chosen as journal cover with nanopatch metasurfaces. And we believe that results may be used by optical researchers and engineers for efficient optimization and designing these metasurfaces for a wide range of applications. That's all. Thank you for your attention.
Thank you for your presentation. Question, please.
Thank you for presentation. I have one question. You had two types of metasurfaces with a rectangular form and a circular form. And in a circular case, you have a specific ellipsoid variant, yes?
Yes, elliptical projection.
If you vary the elliptic form length, smaller, yes, thank you. Smaller and big diameters, how did it change properties of this metasurface?
you maybe means not diameter and radiuses.
Radius,
Yeah,
yes,
yeah.
smaller and bigger.
Yeah, no, as you can see, for anisotropy factor at x, when we change stretch this circle into an ellipse, we have a squeezing factor at y, and we save the area of this circle. That means eta x on eta y equal 1 for all cases when we stretch a circle into an ellipse.
Okay. Am I understand correctly that different configuration of these radiuses for different purposes?
Yes, yes.
Okay, thank you very much.
Thank you. Any questions? We have questions. Thank you for your
Thank you.
presentation. The next speaker, student Oksana Mankovska from Ivan Franko National University of Lviv.
Good day. My name is Oksana Mankovska, and I'm a student from Lviv National University. This work has been done under supervision by Oleg Yermakov from Kharkiv National University and the Leibniz Institute of Photonic Technology. We consider a plane wave incident and the angle theta at the interface between two media. At Brewster's angle, the reflection of TM polarized wave is completely suppressed. In other words, the unpolarized light incident and the Brewster's angle become linearly polarized in the reflection. This phenomenon is widely used in photography, holography, laser technology, etc. However, some specific applications require to shift Brewster's angle closer to easy normal. For example, for polarization filters, anti-reflection coating of solar cells. Besides, the Brewster's angle is used in microscopy to detect the monolayer and also in spin-orbit photonics. At first, we derive the Fresnel equation for the case without 2D layer sandwiches between two media with different referentic indices. We derived them via wave vector approach as opposite to the standard approach with angle of incidence. Here, kzt and kzt are the components of the wave vector along that axis. The total intensity-related reflection and transmission coefficients are defined as the square of the models. After that, we add 2D layer between two media described by surface conductivity sigma. The formulas are modified as follows, and the additional term, including the surface conductivity, appear. The standard formula for Brewster's angle look like this, and one can derive the modified formula, but this formula is approximate and work only for a big contrast between refractive indices. In this work, we derive the exact formula for Brewster's angle, which is always correct. This formula is for the equation that can be solved analytically. To check if it's really possible to shift the Brewster's angle using a two-dimensional layer, we present the following picture. This is the dependence of the reflection coefficients of the angle of incidence and the interface between air and quartz. The dip in reflection spectrum is observed at Brewster's angle corresponding to 55.4 degrees. This is especially noticeable in a logarithmic scale. So when we add a two-dimensional layer, we see Brewster's angle shift, which is clearly visible in a logarithmic scale. At value of surface conductivity of 1 millisiemens, the Brewster's angle shift by around 7-8 degrees. by around 8 degrees. And in more general case, the surface conductivity is complex, while the amplitude can change, but the Brewster's angle position remains the same. So we have shown that sigma works, and now we want to understand what the value of Brewster's angle shift can be for real materials and structure. To do this, we first consider the conductivity of graphene in the terahertz frequency range. It's given by the following formula. The dependence of real and imaginary part look like this. Here the blue line is the real part and the red line is the imaginary part. We also plot the dependence of the reflectant on the frequency and the angle of the incidence. The green line is the standard case for Brewster's angle, and the pink line is the modified Brewster's angle. Next, we have the dependence of the shift of Brewster's angle on a frequency, and we see that at low frequencies, the shift value can reach 16 degrees, which corresponds to the regime where the real part of surface conductivity is large and the imaginary part is low. After that, we consider the surface conductivity of plasmonic metasurface. It's given by the following formula. There, sigma 0 is amplitude, omega is angular frequency, omega 0 is the resonant frequency of the material, gamma is the bandwidth of resonance. A typical dependence of the real and imaginary part look like this. Here, the blue line is the real part, and the red line is the imaginary part. In this color map, we can see the dependence of the reflectance on the value of the frequency and angle of incidence. The green line is the standard case for Brewster's angle, and the pink line is the modified Brewster's angle. We can see that at the lower and higher frequency, the shift of Brewster's angle and the reflection suppression are less than at the resonance owing to the real and imaginary part of conductivity. The shift of Brewster's angle increases with the frequency up to maximum value about 20 degrees, corresponding to the resonance of plasmonic metasurface. The following column map shows the dependence of the value of the Brewster's angle shift in degrees on the frequency. We can see that the angle shift value can reach 20 degrees at the frequency around 500 terahertz. That corresponds to the resonance of plasmonic metasurface. And we want to understand what the value of Brewster's angle shift can be for real design of plasmonic metasurface. We plot the angular dependence of the reflectance, blue line, transmittance, red line, and the absorbance, its yellow line. And the special distribution of the reflectance, its top half plane, and transmittant, bottom half plane magnetic field at the angle of 55.4 and 72 degrees. The first case is without 2D conducting interface corresponds to Fresnel equation. In second case, we add 2D conductive layer of 3.5 millisiemens. The Brewster's angle shift to 72 degrees. Next, we consider the plasmonic metasurface representing the square periodic array of gold nanodiscs. So, to observe the suppression of the reflectant magnetic field at 72 degrees was a case of conducting structures interface. This effect is supported by the absorbent compensation at the level of 40% in the initial intensity. So in this work, we describe the impact of surface conductivity of 2D layer on the shift of Brewster's angle in the angular reflection spectrum. We derive the analytical formula of Brewster's angle for the case of a 2D conducting layer interface and analyzed the cases of a monolayer graphene layer and plasmonic metasurface. And we understand that the Brewster's angle shift can reach values up to 20 degrees. Thank you for your attention.
Thank you for your presentation. Please question.
Thank you for your presentation. The dependence of the Brewster's angle is considered in the terahertz range for the graphene. Is the dependence expected to be preserved for other 2D materials such as transition metal dichalcogenides or others?
In this work, we talk about graphene and plasmonic metasurface, so that's all results.
Any questions?
Thank you for your talk. You considered conductive metasurfaces and conductive layers. Do you think if it is real to achieve similar results with dielectric metasurfaces, or you principally need conductivity?
Yes, we principally need conductivity, and here we talk about the real layer based on gold nanodiscs.
Okay, thank you.
Questions? We have no questions. Thank you for your presentation. And the next speaker, student Artem Yurkov from Karazin Kharkiv National University.
Okay, everybody. So my name is Artem Yurkov, and I am pleased to present you some intermediate results from our research, which is dedicated to surface waves. There is surface waves at anaxial metamaterials covered by resonant anisotropic metasurfaces. Yes, it's malfunctioning. Okay. So as I've said, my work is about surface waves, and unlike the bulk waves, they are bound to the surface and fade evanescently with the rise of the distance. Okay, so far there are two basic models that can support these surface waves that are conductive metasurfaces, or basically conductive surfaces, and uniaxial materials. So the waves supported by these two structures are pretty well studied, for instance, in these works. And the question is what we will receive if we combine them. So to answer this question, we consider this model, which is basically a uniaxial material covered by a conductive surface. The tangential components of permittivity and the conductivity such that they coincide, but it's not necessarily. In our future work, we'll study the case when they are shifted. To perform analysis of the waves occurring at these hybrid structures, we need to receive the equation which governs these surface waves. And we obtain them by pretty conventional methods of sewing the fields in the lower and the upper mediums with boundary conditions and received this equation. Okay, so having this receipt, we can now go to analysis of our waves and compare them with other pretty well-studied system. Let's start with the later. So if we have a simply isotropic medium as a substrate and hyperbolic, in hyperbolic regime, the tangential components of a wave vector of surface waves outside this yellow circle are such that they mimic the view of the field excited. Okay, this case is also pretty well studied. And what will happen if we add uniaxial substrate? So it's obviously then that the parameters of it will influence of our waves. And when the one of components of the permittivity tensor is negative, the light permittivity is such that within this area we have two localized modes. When outside it, we have only one localized mode. And for the same parameters which we considered in the previous case, the field looks also alike. But in case when the wave propagates in both of these areas, then there is something interesting starts to happen. By this I mean that the waves propagating within this range have tangential component of wave vector closer to the light cone than the waves outside this branch. This means that waves within this range angular are easily excited, and the imaginary component of this wave vector, which indicates on fadings, says that waves propagating within this range will fade in 10 times approximately slower than outside it. And this happens also with other regimes. The tendency is the same. And we can expect that we will see our field predominantly in this range. And that is actually what we observed during our numerical analysis of these fields. So we can see that the field is mostly channeled in this angular range. And outside this uniaxial substrate, all the field goes with ellipse, pretty similar to circles, which is not interesting that because in most cases we want the field to be channeled and the energy not to be scattered in all directions. So To sum up what I have said, there are two main things which we done in our research so far, which is we obtained the equation which describes this general case of structure which can support surface waves, which wasn't done previously. And what we saw that there are regimes where we can see the channeling of light, which was also not seen before. Okay, so that's probably all that I wanted to say you. Don't hesitate to ask questions.
Thank you for the questions. Or thank you for your presentation. Any question? I don't see any questions. Thank you presentation again. And it was the last presentation for today. Dear colleagues, thank you for your participation in our third day. We will waiting for you tomorrow for the last day of the conference Nano 2024. Thank you.